Hey guys, tonight we're journeying back to a forgotten world, a time when all the lands of the earth were one, to witness the story of a storm that lasted for 2 million years. Imagine, we are standing in the heart of a continent so vast it beggars belief. The year is 235 million BC. Before you lies nothing. Just a horizon that seems impossibly far away, under a sky that feels too big and empty. The air is hot, thin, and achingly dry. The light from the single ancient sun has a strange, brassy quality you can't quite put your finger on. This is the supercontinent of Pangaea, and you are further from an ocean than any human has ever been. This world is the cradle for everything that comes next, including, in a very distant way, us. But this seemingly stable world, baked into stillness for millennia, is about to be violently undone. It will be drowned by a relentless globe-spanning deluge, its ecosystems shattered, and its dominant rulers pushed to the brink of extinction. And in the chaos, a small, unassuming group of creatures will get the lucky break they need to inherit the Earth. So what could cause it to rain, not for a season, but for 2 million straight years? How does a planet's climate completely flip? And how did this single, long-forgotten storm pave the way for the most famous monsters that ever lived? Thanks to the clues buried deep within the Earth's rock layers, tonight we can piece together the story of this great drowning and watch as a new world is born from the flood. Frankly, if you were dropped here for real without a serious supply of sunscreen and water, you wouldn't last long enough to worry about the giant crocodile cousins. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. It always fascinates me to see where you're all tuning in from. Let me know in the comments where you are in the world and what time it is for you. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Take a slow breath. You're standing on reddish, dusty soil, baked hard under that relentless sun. The silence is profound. It's a silence made of immense distance. There are no birds to sing, no distant hum of traffic. Just the whisper of a hot wind carrying dust that has traveled 1,000 miles to greet you. This is the world of the Middle Triassic, the first chapter of the Mesozoic era, an age that rose from the ashes of the greatest catastrophe life had ever known. This world you're standing in is an afterstory. It's the result of the Great Dying, a mass extinction at the end of the previous period, the Permian, that wiped out over 90% of all marine species and 70% of terrestrial life. Everything alive here is a survivor, a descendant of the very few who made it through. The land itself is a single, colossal entity. From where you stand, you could walk north or south, east or west, and for months you would never see a major body of water. This is Pangaea. It's a sea-shaped behemoth, wrapped around a warm, equatorial sea called the Tethys, while the rest of the planet is covered by a single globe-spanning ocean called Panthalassa. This shape is the key to everything. It is the engine of the world's climate, a climate of extremes. You can almost feel the continent breathing, a slow, planetary rhythm of heat and drought. How do we even know this? How can we map a world that vanished hundreds of millions of years ago? The secret is in the rocks. When volcanic rocks cool and harden, tiny magnetic minerals inside them, like magnetite, align themselves with the Earth's magnetic field at that exact moment. They act like millions of microscopic compasses, frozen in stone, pointing to where the magnetic pole was relative to that rock. By sampling rocks of the same age from different continents and piecing the puzzle together, a science called paleomagnetism, we can rewind the continents and watch them dance back into their ancient embrace. It's this incredible scientific evidence that allows us to picture this world with any confidence, though geologists still debate the exact configuration of Pangaea's northern and southern tips, arguing over the precise coastlines of a world none of us will ever see. This period gets its name, the Triassic, from a much less exotic location than the heart of Pangaea. In the early 19th century, German geologists noted that in their part of the world, the rocks from this age always came in a neat stack of 3 distinct layers: a red sandstone layer, a chalky layer, and a dark shale layer. They called it the Trias. For 3. A simple observation in a German quarry gave a name to this entire alien chapter of Earth's history. It's a quiet reminder that the grandest stories are often pieced together from the humblest of clues. For now, though, you are a long way from those German quarries. You are here in the vast, quiet, and dangerously stable heart of a world waiting for a storm. That storm is still a long way off. For now, the only thing that feels absolute is the heat. It's not the gentle, humid warmth of a tropical island. It's the oppressive, baking heat of an oven. You raise a hand to shield your eyes and look up. The sun seems to burn with a whiter, fiercer intensity in the thin, dry air. The sky itself is a pale, washed-out blue, a stark canvas holding that single, blistering point of light. The ground beneath your feet isn't just warm, it's hot to the touch. A vast expanse of rust-colored dirt and cracked mudstone polygons that stretch to a hazy, shimmering horizon. There is no softness here. Even the plants are defensive, huddled low to the ground with waxy, needle-like leaves designed to hoard every precious drop of moisture. They look more like sculptures of life than living things. You can taste the dust on your tongue. It's a fine, gritty powder that coats everything, a silent testament to a world starved of water. This is the great planetary engine of Pangaea at work. The sheer size of the continent creates a climate of unimaginable extremity, a phenomenon scientists call continentality. The coasts, thousands of miles away, are lashed by a powerful Mega-Monsoon system. In the summer, the vast landmass heats up faster than the surrounding Panthalassan ocean, creating a low-pressure zone that pulls in immense quantities of moisture. Those coastal regions are drenched with seasonal rains, but you are in the deep interior, shielded by sheer distance. Those life-giving clouds exhaust themselves long before they can reach you, leaving the heart of the continent in a permanent, continent-sized rain shadow. This is the great truth of the Triassic world, a fact written into its very geology. Much of the Earth's landmass during this period was covered by deserts, sprawling dune seas larger than the Sahara, Gobi, and all other modern deserts combined. When you look at the rock record from this time, you find thick, sweeping layers of what are called red beds. This is the scientific evidence for this world you're standing in. These are ancient desert sandstones, their grains of sand stained a deep crimson by the slow rusting of iron minerals. For iron to oxidize like that, it needs to be exposed to air over long, dry periods. Interspersed with these fossilized dunes are wide, white pans of evaporites, the layers of salt and gypsum left behind when the occasional temporary lake would appear and then swiftly vanish under the relentless sun. The rocks don't lie. They tell a story of dryness, of heat, and of time stretching on for millions of years. Life here is tuned to this harsh rhythm. Everything is either an expert at finding water or an expert at living without it. During the day, most animals are hidden. They are tucked away in deep burrows where the earth remains cool, waiting for the brief reprieve of dusk. Life is a patient game of endurance, and as the sun finally begins to dip, painting the dusty sky in shades of orange and violet, you might see some of that life emerge. You might spot a strange, stout creature about the size of a badger, cautiously sniffing the air. It's covered in leathery skin or maybe some bristly fur, with a short tail and powerful digging claws. This is a Traversodont Cynodont, a distant relative of yours and mine on the great tree of life. You could almost call it a Triassic nightmare squirrel. They have surprisingly complex, molar-like teeth designed for grinding up tough plant matter, a hint of the mammalian efficiency that is still 100 million years in the future. They are the survivors, the specialists of the drylands. Yet even in this bone-dry world, there is a pulse of water. It's just faint and far between. Perhaps once a year, or once a decade, the Mega-Monsoon pushes a little harder, and a few stray storm clouds will make it this far inland. The result isn't a gentle shower, but a violent, short-lived deluge that turns the dry landscape into a chaos of flash floods. For a few frantic weeks, the world turns to mud. The plants explode in a riot of brief, desperate growth, and the animals rush to breed and feed. Then, just as quickly, the water is gone, and the long, patient silence of the drought returns. This is the delicate, brutal balance of life in the heart of Pangaea. And while the evidence for this arid interior is overwhelming, paleoclimatologists argue about the severity of the Triassic mega-monsoons and how far inland their influence was truly felt. Were these brief floods a regular yearly event even here in the deep desert, or were they rare, once-in-a-century flukes? The truth is, we are still learning the precise heartbeat of this long-lost world. As twilight deepens, the brutal heat of the day finally begins to bleed out of the landscape. The air cools, and a deep stillness settles over the red earth. This is the witching hour of the Triassic, the time when the world truly wakes up. And as you scan the horizon, you see a shape detach itself from the deepening shadows. It's large, low-slung, and it moves with a ponderous, deliberate confidence. Your mind, conditioned by a lifetime of popular culture, immediately leaps to one conclusion. It's a dinosaur, but your mind is wrong. What you are looking at is something older, something that was the undisputed master of this world long before the first tyrannosaur ever hatched. You are looking at a Crurotarsan. This is the great forgotten dynasty of the Triassic. They are Archosaurs, the ruling reptiles, just like the dinosaurs, but they belong to a different branch of the family tree. This is a crucial point, a fundamental fork in the road of life's deep history. Millions of years before you arrived here, the ancestral Archosaurs split into two great lineages. It's one of the most important divergences in vertebrate history. One branch, the Avametatarsalia, went on to produce the pterosaurs, the dinosaurs, and eventually, the birds. The other branch, the Pseudosuchia, often called the Crurotarsi, evolved into the incredible diversity of crocodile-line reptiles that ruled this arid world. You are looking at the winning team. The creature before you is a Postosuchus, a perfect embodiment of Crurotarsan dominance. It's about 20 feet long, a walking nightmare with the oversized, heavily built skull of a crocodile, studded with teeth like serrated daggers. Its back is armored with rows of bony plates, or scutes, embedded in its thick, scaly hide. But what's most surprising is its posture. It's not sprawling like a modern croc. Its powerful legs are held almost directly beneath its body, holding its heavy torso high off the ground. It moves with a swaggering, surprisingly agile gait, a far more active and terrestrial predator than its swamp-dwelling relatives of the modern day. The scientific evidence for this comes not just from their skeletons, but from the fossilized footprints they left behind. Triassic trackways show the narrow, purposeful stride of an animal with an erect posture, their feet falling nearly in a straight line, a stark contrast to the wide, dragging gait of a sprawling reptile. Postosuchus raises its massive head and tastes the air with its tongue. It is the apex predator of this environment, the Triassic equivalent of a grizzly bear or a Bengal tiger. Everything that lives and breathes in this dry world does so at its pleasure. But it's just one member of a thriving and varied clan. Elsewhere on the continent you would find the Dinosaurs, herbivorous Crurotarsans built like walking tanks. Their bodies so heavily armored, they look like reptilian pine cones. You'd also find the Phytosaurs, who so perfectly resemble modern crocodiles that it's one of the most stunning examples of convergent evolution in the fossil record. And then there were the true oddballs. Paleontologists have found some Crurotarsans, like Ephidia, that were bipedal, long-legged, beaked, and completely toothless. They looked and likely acted just like the famous ostrich-mimic dinosaurs, but they came from the crocodile side of the family. It was a bizarre evolutionary experiment, proof that nature often stumbles upon the same good ideas from completely different starting points. These were the rulers, the kings and queens of Pangaea. They filled every major ecological niche. They were the big predators, the armored herbivores, the semi-aquatic ambushers, and even the speedy ostrich-like runners. Their success is written in stone all across this planet. And the creature in front of you, the mighty Postosuchus, is the ultimate expression of that success. Still, for all that we know, there is so much that remains a mystery. The exact posture and metabolism of animals like Postosuchus is still a topic of intense discussion. Were they sluggish, cold-blooded ambush predators that relied on the blistering sun to power their attacks? Or were they something more, active pursuit hunters with a higher metabolism that allowed them to dominate the landscape day and night? We see their bones, we see their tracks, but the vital spark of their life is a secret the Triassic keeps to itself. For now, all you know is that you are in the presence of royalty. In this world, dinosaurs are little more than pests, small, scurrying creatures in the undergrowth, living in the shadows of these true giants. The great predator, the Postosuchus, moves on into the gloom, a silent passing shadow of immense power. It is the king, but a kingdom is nothing without subjects. An ecosystem cannot be built on predators alone. For a giant carnivore like that to thrive, it needs a vast and reliable source of food. And now, as the last light of day fades, the buffet begins to emerge. You see them first as a low, lumbering herd, moving out from the shelter of a rocky outcrop. They are the true backbone of this Triassic world. They are the grazers, the browsers, the plant-eaters. They are the tusked and the beaked masses. Your eyes are drawn to the largest among them. These are the Dicynodonts. A herd of them, perhaps a species like Placoreas, is an odd sight. They are built like barrels, with stout, powerful limbs that sprawl out to the sides in a way that is neither fully reptilian nor quite mammalian. Their heads are short and broad, ending in a horny, turtle-like beak, but from the upper jaw of the males jut two prominent tusks, like those of a walrus. They are synapsids, which means that for all their scaly, reptilian appearance, they belong to the great lineage of life that would eventually lead to mammals. They are, in the most distant and convoluted sense, your cousins. And in this moment in time, your family is doing incredibly well. The Dicynodonts are a story of profound success, a dynasty of survivors. Their ancestors, like the famous Lystrosaurus, had weathered the storm of the Great Dying at the end of the Permian. In that blasted, empty world, Lystrosaurus became so numerous, so widespread, that for a time it was the single most common land vertebrate on the entire planet. The creatures before you now, the larger Placerias, are the heirs to that legacy of toughness. They are living proof that you don't have to be fast or flashy to succeed. You just have to be good at what you do. And what they do is eat. Their powerful beaks can snip through the tough, woody plants that other herbivores can't manage. Their tusks, often the only teeth they possess, are used for digging up nutritious roots and tubers, and perhaps for display or defense. It's a quirky and effective combination. This simple body plan was so successful that Dicynodonts became one of the first truly globally distributed groups of large land animals. Their fossils have been found on every modern continent, from the plains of Africa to the frozen wastes of Antarctica, which was then a temperate part of the great Pangaean landmass. We can even get a glimpse into their very metabolism through the microscopic details of their bones. The scientific evidence from bone histology, the study of bone tissue structure, shows a pattern of rapid, sustained growth. When you slice their fossilized bones into paper-thin sections, you can see a structure more akin to that of a fast-growing mammal than a typical slow-growing reptile. This suggests they weren't sluggish, basking creatures. They were active, energetic animals that fueled their lives with a constant intake of tough vegetation. Still, for all we know, their outward appearance remains a mystery. Whether Dicynodonts were covered in scales, leathery skin like a rhinoceros, or patches of bristly primitive hair is something paleontologists have yet to agree on, a detail lost to the millions of years. Moving among the larger Dicynodonts are the other great herbivores of the age, the Rhynchosaurs. They are lower to the ground, squat and powerful, with enormous beaked heads that seem too large for their bodies. They are the ultimate specialists. Their jaws don't have teeth in the way we think of them, but rather broad, ever-growing tooth plates that would slice against each other like a pair of self-sharpening garden shears. They were perfectly designed to dig up and process the toughest of roots and stems. Together, these two great groups, the Dicynodonts and the Rhynchosaurs, form the vast, moving herds that define this landscape. They are the lawn mowers of the Triassic. Their constant, placid grazing is the engine that converts the tough, dry plant life into protein, powering the entire ecosystem. They are the reason the Postosuchus can exist. This is a world in balance, a complex and stable system perfected over millions of years of dry, predictable stillness. The placid herds of Dicynodonts and Rhynchosaurs dominate the landscape, their slow, methodical munching the only sound in the cool night air. They are the picture of stability, of an ecosystem running on ancient, predictable rhythms. But then you catch a flicker of movement at the edge of the herd. It's not the heavy, confident tread of a Postosuchus, nor the ponderous shuffle of a Dicynodont. This is something different. It's fast, nervous, and light on its feet. Darting out from behind a sparse, fossilized tree stump is a creature no bigger than a greyhound. It runs on two long, slender legs, its body held horizontally, a long tail streaming out behind it for balance. This is a dinosaur. You are looking at something like an Eoraptor, the dawn plunderer. And it is, to be frank, utterly underwhelming. Its head is small and pointed, its hands have nimble, grasping fingers, and its eyes are large and alert. It moves with a bird-like skittishness, a stark contrast to the lumbering royalty of this era. It picks its way carefully through the landscape, perhaps snatching an insect, or maybe a tiny sleeping lizard. This is the great secret of the Triassic. The creatures that would one day define the word monster began their journey as marginal, almost invisible players. They are living in the cracks of this world, occupying the niches that the great Crurotarsans are too big and bulky to bother with. They are not destined for greatness. They are the underdogs. If you could travel back in time and place a bet on which group would inherit the Earth, you would never choose these creatures. They are overshadowed in every way. For every one of them, there are 100 Dicynodonts. For every pound they weigh, the local Postosuchus weighs 1,000. But they have a few secret weapons, subtle evolutionary advantages hidden away in their anatomy. The most important of these is in their hips. The scientific evidence for what makes a dinosaur is a deceptively simple piece of engineering: an open hip socket. In every other reptile, the head of the femur, the thigh bone, fits into a shallow, cup-like socket on the side of the pelvis. But in dinosaurs, that socket is a complete hole, allowing the leg to be positioned directly and vertically under the body. This pillar-like stance is incredibly efficient for running and, crucially, for breathing while running. It's a blueprint for stamina and agility. This efficient posture was likely linked to an equally efficient respiratory system, a precursor to the one-way airflow that makes modern birds the most powerful endurance athletes on the planet. These subtle tweaks, hidden deep within their skeletons, are the only hint of their future potential. But for now, it just makes them good at being small, fast, and staying out of the way. It's a quiet reminder that evolution doesn't plan ahead, it just finds solutions for the problems of the present. The name we give them, dinosaur, feels absurdly grand for the creature you see before you. It's a quirky accident of history. When the term was coined by the British anatomist Sir Richard Owen in 1842, he was looking at the massive, fragmented bones of Jurassic giants like Megalosaurus. He imagined them as terrible lizards, colossal dragon-like beasts. He never saw these early, scrappy pioneers. The grand, imposing name was given to their swaggering 10-ton descendants. It was never meant for these fleet-footed opportunists. The earliest true dinosaur fossils, like the one you're watching, are found in the rock layers of what is now Argentina and Brazil. During the Triassic, this part of Pangaea was a bit more temperate and humid, a little slice of relative paradise that may have served as the crucible for their evolution. Even with these fossils, so much about their origins remains hazy. Paleontologists still fiercely debate whether the very first dinosaurs were carnivores, hunters of small prey, or if they were omnivores, surviving on a mixed diet of plants, insects, and anything else they could get their claws on. This debate shapes our entire understanding of the initial evolutionary pressures that forged this legendary group. For now, the little dinosaur snatches one last insect from the air and darts back into the shadows, a fleeting and insignificant ghost. It is a minor character in a story dominated by giants, a flicker of an idea in a world that has no time for it. There is no sign, no omen, no hint in the dry Triassic air that you have just laid eyes on the beginning of a dynasty that will one day rule the world for 150 million years. The little dinosaur vanishes, and the deep, profound silence of the Triassic night returns. The world feels ancient, stable, locked in its rhythms. It feels like it will go on like this forever. But then, you feel something. It's not a sound, not at first. It's a vibration, a deep, low-frequency hum that seems to be coming from the very bones of the planet. You feel it in the soles of your feet, a persistent tremor that is so constant it almost becomes a part of the silence. It's not an earthquake. It lacks the sudden violence. This is a planetary hum, the thrumming of a world-sized engine slowly, unstoppably turning over. The source of this vibration is thousands of miles to the north, in the part of Pangaea that will one day become Alaska and British Columbia. And what is happening there is not a volcano. You must erase the image of a single, conical mountain spewing ash. This is something far more vast and far more sinister. This is a large igneous province, or LIP. The Earth's crust in this region is giving way, splitting open along immense fissures that are hundreds of miles long. It is not exploding. It is bleeding. The planet has a fever, and this is the symptom. From these colossal cracks in the ground, lava is welling up. Not in a dramatic fountain, but in a vast, silent, inexorable flood of molten rock that pours across the landscape, burying everything it touches. You are too far away to see the fire itself, but you can see its ghost. As you look to the northern horizon, you notice the stars are gone. The sky there doesn't have the inky blackness of the sky above you. Instead, it has a faint, permanent, dull red glow. It looks like the light from a city that is perpetually on fire, just over the edge of the world. It is the reflection of an ocean of lava, painting the undersides of the high clouds in a color of rust and blood. This glow and the hum you feel in your bones will not stop for the night. They will not stop for a year or a century or a millennium. They will continue, unabated, for 5 million years. The scale is almost impossible to comprehend. Over those 5 million years, this event, what geologists call the Wrangellian eruptions, will pour out enough lava to cover an area the size of Texas and Alaska combined. The layers of basalt rock it leaves behind will be, in places, 6 kilometers thick. That's a pile of hardened lava taller than Denali. This is the calling card of the planet's great killers. Large igneous provinces are not a freak event. They are a recurring feature in Earth's history, and their appearance in the geological record is often associated with the darkest chapters in the story of life. It's this kind of relentless, planetary-scale volcanism that is implicated in several of Earth's worst mass extinctions, including the Great Dying that preceded this era and the one that is yet to come at the end of the Triassic. The name for this particular apocalypse is, as is often the case in geology, deceptively mundane. It is called Wrangellia, named after the Wrangell Mountains in modern-day Alaska, a place where these immense layers of ancient, dark, volcanic rock are beautifully exposed for us to study. And we have studied them. The scientific evidence for the timing and duration of this event comes from the patient work of geochemists using the planet's own atomic clocks. Certain elements trapped in the cooling lava, like uranium, decay into other elements, like lead, at a perfectly steady and known rate. By measuring the precise ratio of uranium to lead in these rocks, we can calculate their age with astonishing accuracy. And these atomic clocks confirm that the eruptions were not a single sudden cataclysm, but a continuous, slow-burn catastrophe that began 235 million years ago. The lava itself, for all its terrifying scale, is not the true killer. The lava is just the symptom. The real weapons of a LI are the gases, the immense volumes of carbon dioxide, sulfur dioxide, and other poisons that are exhaled from the planet's interior along with the molten rock. And here, a great mystery remains. Scientists still argue whether the main killing agent of LIPS is the CO2, which triggers runaway global warming, the sulfur dioxide, which creates devastating acid rain, or the cocktail of heavy metals like mercury that are vaporized and spread globally. The hum in the earth is the sound of a gun being slowly cocked. The world you're standing in has no idea that its fate is being sealed by that faint, ominous glow on the horizon. That faint, ominous glow on the horizon is the furnace. The hum in the earth is the engine. But the weapon, the true agent of the change that is coming, is invisible. It is tasteless and odorless. It is leaking from those fissures in the north, and is slowly, inexorably wrapping itself around the entire globe. You can't see it, but you can start to feel its effects. The air itself is changing. The stable, predictable world of the Triassic is beginning to suffocate under a blanket of its own making. The primary poison is carbon dioxide. For every ton of lava that floods the land in the north, tons of CO2 are being released from the planet's mantle into the sky. And this gas is beginning to fundamentally rewrite the Earth's energy budget. Normally, the planet maintains a delicate balance, with heat from the sun arriving and then radiating back out into space. The CO2 disrupts this balance. It acts like a one-way mirror, or the glass of a greenhouse, letting the sun's warmth in but refusing to let it leave. With every century that passes, the Wrangellian eruptions pump more and more of this gas into the atmosphere, and the thermal blanket gets thicker and thicker. The planet is being slowly cooked, with global temperatures set to rise by an average of 3, maybe 5, perhaps even 10 degrees Celsius. You feel this change not as a sudden blast, but as a creeping, oppressive warmth. The nights no longer bring relief from the day's heat. A humid, heavy quality begins to infuse the air, which now feels thick in your lungs. A deep breath doesn't feel quite as refreshing as it should. The established arid climate is being destabilized, and with the CO2 comes another more aggressive poison, sulfur dioxide. This gas reacts with sunlight and atmospheric moisture to create a thick, hazy veil of volcanic smog, or VOG. The sky, which was once a crisp, pale blue, takes on a milky, yellowish tint. The sunsets become spectacular, a riot of lurid oranges and purples as the light scatters through the aerosol-choked air. But it's the beauty of a fever dream. And when this sulfur dioxide mixes with water vapor, it becomes sulfuric acid. On the coasts, thousands of miles away, the first bouts of acid rain are beginning to fall, turning pristine freshwater lakes into toxic, sterile pools. The sheer volume of gas is staggering. The concentration of CO2 in the atmosphere during this time may have exceeded 4,000 parts per million. For context, our modern climate-changed atmosphere is currently hovering around 420 parts per million. This was a supercharged greenhouse world. We can read the signature of this ancient pollution directly from the fossil record. This is the scientific evidence, a chemical fingerprint left at the scene of the crime. Volcanic carbon has a slightly different atomic weight, a different isotopic signature than carbon from other sources. By analyzing the ratio of these carbon isotopes, the delta 13C, in fossilized soils and the remains of plants from this period, scientists can see a massive, worldwide spike in volcanic carbon, confirming that the air itself was saturated with the breath of the Wrangellian eruptions. Ironically, for some life, this overdose of CO2 was a blessing. Carbon dioxide is, after all, plant food. And in a quirky twist, early geologists mapping the Wrangellia lava fields were baffled to find thick seams of coal directly on top of the hardened basalt. It was a paradox, a scene of fiery destruction immediately followed by a lush, thriving forest. These were the disaster forests, opportunistic ecosystems that sprang up in the north, thriving in the warm, wet, high CO2 conditions created by the very volcanoes that would eventually cause a global crisis. It's a testament to the strange resilience of life, and a warning that a planetary system under stress can have complex and contradictory effects. But this boom in plant life in the far north is just a local symptom. For the planet as a whole, the fever is rising, and how quickly the global temperature rose in response to the Wrangellian outgassing is a key variable that climate modelers are still trying to refine. Was it a slow, steady climb, or did the system lurch upwards in a series of abrupt, shocking heat waves? The animals of the Triassic, going about their lives, have no idea that the very sky is turning against them. The rules of their world are being rewritten by a poison they cannot see. The poisoned sky is the first symptom of the planet's illness, but the sickness isn't confined to the air. It is seeping, slowly but surely, into the greatest reservoir of life on Earth, the ocean. Let's leave the dusty, baked interior of Pangaea for a moment. We're moving, traveling thousands of miles to the east, to the shores of the great, world-spanning ocean, Panthalassa. You are standing on a black, volcanic cliff, and before you is a body of water so vast it seems infinite. The hazy, yellow-tinged sky you saw in the interior hangs over the water here too, and the sea itself has a strange, glassy stillness. It looks peaceful, but it is a deeply deceptive peace. The ocean is dying from the inside out. It is being attacked by a trio of silent, invisible killers. The first is heat. Just as the atmosphere is warming, so too is the ocean. It is the world's great heat sink, absorbing monumental amounts of warmth from the overloaded greenhouse above. The surface water, which should be merely warm, feels like bath water. This excess heat is the first shock to the system, stressing every creature that lives within it. The second killer is acidification. The ocean is acting like a giant sponge, soaking up as much of that excess carbon dioxide as it can. When CO2 dissolves in water, it forms carbonic acid. The chemistry of the entire ocean is beginning to shift. It's a slow, planetary-scale version of turning fresh water into sparkling water. The sea is becoming ever so slightly more corrosive. For you, this change is imperceptible. But for the creatures that live here, it is a catastrophe. Life in the ocean has spent hundreds of millions of years evolving to thrive in a chemically stable environment. Now that stability is gone. The first to suffer are the reef builders. The Triassic was a critical time for the evolution of modern stony corals, the group known as Scleractinians. After the devastation of the Permian extinction, they were just beginning to build the first true coral reefs the world had seen in millions of years. But their skeletons are made of calcium carbonate, a mineral that is incredibly sensitive to acidity. As the ocean acidifies, the corals can no longer pull the building blocks they need from the water. They begin to bleach, expelling the vibrant algae that live within them, turning a ghostly white before they starve and die. You can see their pale skeletons shimmering in the unnaturally clear, warm water, an ancient echo of a climate crisis we are tragically familiar with today. What's happening to the corals is also happening to countless other creatures. The beautiful spiraled ammonites, shelled relatives of the squid, find it harder to build their intricate shells. The tiny plankton at the base of the food web struggle. The entire chemical foundation of marine life is starting to dissolve. We can see the global nature of this crisis in the rock record. The scientific evidence comes from the limestone laid down on the seafloor during this time. Geochemists have analyzed its chemistry, and they found the exact same negative carbon isotope excursion, the same fingerprint of volcanic CO2, that was found in the fossilized soils on land. It is the ultimate proof that the gas from the Wrangellian eruptions saturated the entire planet, from the heart of the continent to the deepest ocean. The third killer is anoxia. The warmer the water gets, the less dissolved oxygen it can hold. The ocean is, in essence, beginning to hold its breath. In the depths, vast zones completely devoid of oxygen are starting to form. They are suffocating, dead zones where only the simplest bacteria can survive. Any fish or marine reptile that wanders into them will perish. Among the victims of this multifaceted assault were the Dicynodonts, a quirky and mysterious group of eel-like creatures. For most of their history, all we knew of them were their bizarre and microscopic tooth-like fossils. These tiny, intricate fossils are so common and evolved so quickly that for decades, geologists have used them as critical index fossils to determine the age of rocks. This oceanic crisis decimated the Dicynodonts, pushing them to the brink from which they would never recover, eventually going extinct at the end of the Triassic. Heat, acidification, and anoxia, a triple threat. And so, a great scientific question remains. Whether the marine extinction was primarily caused by acidification, anoxia, or temperature stress is a complex problem, and the answer likely varies by region and by species. Was it the heat that killed the corals? The acid that killed the ammonites? The lack of oxygen that killed the fish? Or was it simply the devastating, combined shock of all three at once? As you look out at the vast, sick ocean, you realize the full, terrifying scope of the problem. The disease that began as a fever deep within the earth now infects the sky and the sea. The entire planetary system is failing. The sickness of the ocean feels a world away, but it is not. In a complex planetary system, nothing is truly separate. The fever of the sea is about to become the fever of the land. We are traveling back now, leaving the coast behind and returning to the deep, arid heart of Pangaea, where our journey began. But something is profoundly different. The air that was once so thin and dry is now heavy, thick with a humidity that feels alien to this desert landscape. The heat is no longer the clean, baking heat of an oven. It's the wet, suffocating heat of a steam room. Every breath is a thick, warm gulp of air that feels too full of water. All the pieces are now in place. The long, slow process that began with a hum in the earth is reaching its climax. The planet has been primed for a catastrophe. Think of it as a loaded gun. The Wrangellian eruptions, pumping out colossal quantities of CO2, have created a superheated greenhouse world. That is the gunpowder. The vast Panthalassan ocean, warmed by this new heat, is now evaporating at a furious rate, pumping trillions of tons of water vapor into the atmosphere. That is the bullet. And the atmosphere itself, now so warm it can hold more moisture than ever before in its history, is the chamber. The gun is loaded. The planet's finger is on the trigger. The old weather patterns, the ones that had defined this world for millions of years, are breaking down. The traditional Mega-Monsoon, which had always been confined to the coasts, is being supercharged by the heat and moisture. It is becoming stronger, more violent, and is beginning to push further and further into the continent's interior. We know this isn't just speculation. This is what the physics of climate demands. Modern scientific evidence for this comes from sophisticated climate models. When scientists build a simulation of the Triassic world on a supercomputer and allow it to run, it perfectly reproduces the arid interior. But when they begin to pump up the atmospheric CO2 levels to match the output of the Wrangellian eruptions, the models consistently show the monsoon system intensifying dramatically, driving moisture deep into the continental heart. The simulations predict a deluge. This very concept, that a period of intense global warming could trigger a long-lasting pluvial or rainy period, is a historical fact that has profound implications for us today, as it's a major area of study for scientists trying to understand the full range of possibilities in our own planet's future. The event we are about to witness is sometimes known by a gentler, more poetic name than the Carnian Pluvial episode. Some researchers have called it the wet intermezzo, a name that beautifully captures its character. Intermezzo is Italian for interval, and that's precisely what this was. A brief, shockingly wet chapter in the middle of a long, otherwise dry book. You are standing in the final days of the dry world. You look up at the sky, but you can't see the sun. There are no clouds, not in the way you think of them. There are no puffy, distinct shapes. Instead, the entire sky is a single, luminous, milky white sheet. The air is so thick with moisture and aerosols that it has become a universal, featureless haze. The silence is different now. It is not the peaceful silence of a dry desert night. It is a heavy, ringing silence, full of pressure and unspoken tension. The animals are gone. They are hiding in their burrows, sensing the immense wrongness of the atmosphere. The world is holding its breath. We know all the ingredients for the flood are present. We know the system is at a breaking point. But the final, precise trigger remains a tantalizing mystery. Precisely what atmospheric or oceanic circulation pattern finally broke, allowing the moisture to penetrate the entire continent, is the final piece of the puzzle that researchers are still fitting together. Was it a shift in the jet stream? A change in the ocean's currents? We may never know. All you know is that here, in the final moments of the old world, the air itself has become water waiting to happen. The first drop is coming. The world holds its breath, and then it happens. A single heavy drop of water, warm as blood, strikes the dusty ground in front of you. It makes a dark, star-shaped crater in the red dust. Another follows, then a third. And then the sky, that luminous milky white ceiling, seems to dissolve all at once. There is no gentle build-up, no introductory shower. The deluge begins as a solid, roaring wall of water, a vertical flood falling from the sky. It is a storm of tropical, perhaps even extraterrestrial, violence. The sound is deafening, a continuous percussive roar that drowns out all other senses. The air, which was hot and still, is instantly charged with the sharp, clean scent of ozone from the colossal lightning strikes that begin to tear the sky apart. You can smell the petrichor, the scent of rain on dry earth, but it's an aroma on a planetary scale, an exhalation from a continent that hasn't known a true soaking in millennia. The first drops to hit your skin are a shock, not of cold, but of coolness against the oppressive heat. Within moments, you are drenched, and the ground itself is transforming. The hard-baked dust and cracked mud are churned into a thick, running slurry of red mud. The initial violence of the storm is a spectacle of raw, untethered power. Lightning flashes not as distinct bolts, but in strobing silent sheets that illuminate a world in chaos. The thunder is not a distant rumble. It is a concussive, physical blast that you feel in your chest, as if the very firmament is cracking open. The animals which had been hiding are now in a panic. Small, burrowing creatures are flooded from their homes, scrambling for higher ground that no longer exists. The great herds of Dicynodonts and Wrangellian caught out on the open plains are confused and terrified, huddling together against a force of nature they cannot comprehend. A normal storm, even a violent one, eventually blows itself out. But this one does not. The first day of rain bleeds into the second, and then the third. The initial, terrifying violence may lessen, but it is replaced by something almost worse. A relentless, monotonous, heavy downpour that simply does not stop. The sun is gone, a forgotten memory behind a permanent veil of churning, bruised grey clouds. The distinction between day and night blurs into a perpetual, watery twilight. A week passes, then another. The landscape is being unmade. The ancient dry riverbeds, the wadis that might have seen a flash flood once a century, are now unrecognizable. They have become immense, raging torrents, rivers of liquid mud the color of rust, carrying boulders and uprooted, fossilized trees in their churning currents. This is the moment that is forever captured in the geological record. This is the boundary. The scientific evidence for this event is stark and beautiful in its clarity. In places all around the world where this layer of time is exposed, you can see it. You can lay your hand on it. Layers of red, wind-blown desert sandstone, representing millions of years of arid stability, come to an abrupt, clean end. And directly on top of them, with no transition, begins a thick, dark layer of grey, water-lain rock, mudstones, shales, and conglomerates full of jumbled, water-worn pebbles. It is a line in the rock that tells the story of a world that changed overnight. This entire concept, the story of this 2-million-year reign, is a surprisingly recent discovery. For more than a century, geologists had noted these strange, out-of-place, wet-climate rocks in the middle of the dry Triassic, but they were often dismissed as local anomalies. It was only in the 1990s that a few British geologists began to connect the dots, realizing that these deposits were of the same age and were found all over the world, signaling a single global event. For all its geological significance, this event is simply known as a sub-stage of the Carnian, one of the ages of the late Triassic. It's a formal, almost bureaucratic name for a planetary apocalypse. And while the story I'm telling you is of a sudden, dramatic shift, it's worth noting that scientists still debate the true pace of this change. Whether the onset of the CPE was a gradual increase over thousands of years or a very abrupt tipping point style change over a few centuries is still debated. But for the creatures on the ground, the effect was the same. The world they knew is gone, washed away, and the rain keeps falling. The years begin to pass. The rain does not relent. What began as a crisis, a shocking and violent event, is now simply the climate. It is the only reality. The memory of a hot sun and a dry breeze is a ghost, a myth from a lost world. And under the ceaseless life-giving water, the planet is transforming. The color of the world is changing. The vast, monotonous reds and browns of the Pangaean desert are vanishing, buried under a tide of relentless green. At first, it's a desperate, opportunistic green. The spores of ferns and horsetails, ancient plants that had clung on in the few damp refuges of the dry times, now find a world made in their image. They explode across the muddy plains. Within a few decades, the landscape is choked with them. Vast primordial fern prairies stretch from one misty horizon to the other, broken only by the murky brown water of the newly born rivers and swamps. It is a world cloaked in a single deep shade of viridian. But this is only the first phase of the great floral revolution. A second, slower and more profound change is taking root. The real winners of this new, wet world are the conifers. Before the rains, they were a minor group, often stunted, scrubby trees confined to the slightly wetter uplands. Now, with unlimited water and a sky rich in carbon dioxide, they begin to conquer the globe. Tall, woody, fibrous trees. Ancestors of modern pines, cypresses, and the strange araucaria or monkey puzzle trees start to rise above the fern carpet. They grow tall and fast, creating vast, dark forests where there was once only open, baked earth. This is more than just a change in scenery. It is a fundamental restructuring of the entire ecosystem. The world now has a vertical dimension it lacked before. It is a world of shadows, of damp, dark forest floors, and of towering, woody trunks. The sensory palette of the planet has been completely repainted. The dominant color is no longer the red of desert dust, but the deep green of pine needles, the dark brown of wet bark, and the permanent oppressive gray of the ever-present clouds. The soundscape has changed, too. The profound silence of the desert has been replaced by the gentle, constant white noise of water. There is the soft, percussive dripping from countless leaves, the gentle gurgle of 1,000 newly born streams, and the soft squelch and suck of your feet in the ever-present mud. And the smell. The air is thick with the rich, loamy scent of damp earth, the sweet, musty aroma of rot and decay from the forest floor, and the sharp, clean, resinous tang of pine. It is the smell of a world being reborn as a temperate, global rainforest. The scientific evidence for this dramatic floral takeover is microscopic, but irrefutable. It comes from the science of palynology, the study of fossilized pollen and spores. Pollen grains are incredibly tough, and they fossilize beautifully, each one a perfect miniature signature of the plant that made it. When scientists analyze the rocks laid down just before the rain began, they find pollen from plants adapted to dry conditions. But in the rocks from the CPE, that pollen vanishes, and there is a sudden massive spike in the fossil record, a spore spike of fern spores. followed swiftly by an overwhelming abundance of conifer pollen. It is the fingerprint of a world turning from red to green. Many of the trees that make up these new forests would be vaguely familiar to us. In fact, many modern conifer families, including the Pangaea family, which includes pines and firs, and the Cupressaceae family, cypresses and redwoods, have their evolutionary origins in this very turnover. A dynasty of trees born from a crisis. Among them grew some evolutionary oddities, like the Bennetit tails. These were plants that looked a bit like modern cycads, but they produced bizarre, complex structures that looked remarkably like flowers. It was a false start for flowering plants, an evolutionary experiment that would eventually fade away, millions of years before true flowers finally appeared. This explosion of green begs a crucial question, one that is still a topic of active research. To what extent this floral shift was driven directly by the increased rainfall versus the increased CO2, which acts as a fertilizer for plants, is an ongoing area of research. Was it the water alone that allowed the forests to spread? Or did the super-fertilized CO2-rich atmosphere play an equal or even greater role? It was likely a combination of both, a perfect storm of conditions for a global forest. The old world is gone. This new gray and green world of forests and swamps will demand a new kind of animal to master it. And the old guard, the masters of the dry, are now strangers in their own, very wet land. The new great forests are the most visible sign of the planet's transformation. But the change that is happening is more than just skin deep. The rain is not just giving life. It is moving mountains. Or rather, it is unmaking a continent, one grain of sand at a time. The very ground beneath your feet is being dissolved and carried away. The ancient, flat, and stable plains of Pangaea, which had endured for millions of years, are being carved up and washed out to sea. This is geological time, but it is happening at a terrifying, accelerated rate. Imagine you find a small, trickling rill of water, a tiny stream cutting its path through the mud. You watch it for a year, and it becomes a small gully. You watch for a decade, and the gully becomes a deep, rushing channel. You watch for a century, a single human lifetime, and that channel has become a roaring, steep-walled canyon. Now, multiply that process by every square mile of a supercontinent and continue it for 2 million years. You are witnessing landscape creation on fast forward. The relentless heavy rain is a tool of immense power, and it is using that power to scar and dissect the land. Vast, powerful river systems are being born, continent-spanning arteries of brown, sediment-choked water. They are nothing like the gentle, meandering rivers you might picture. These are violent Triassic torrents, their waters thick with the eroded soil of the old world. They carry the ghosts of the great dry, the red dust, the sand, the gravel, on a one-way journey towards the sea. The world is in a constant state of flux, its very topography being rewritten with every passing century. And as these powerful rivers flow across the land, they begin to dump their heavy loads, creating the very rock layers that tell us this story. This is the heart of the scientific evidence. As a river loses energy, it can no longer carry the heaviest debris. The largest pebbles and gravel it has been dragging along are dropped first, forming thick, jumbled layers of what geologists call conglomerate. You can think of it as a kind of naturally formed, messy concrete. The finer materials, the sand and silt, are carried further. eventually settling at the bottom of vast, newly formed lakes or in the slower-moving floodplains, creating layers of sandstone and mudstone. These grey, water-lane rocks are the physical embodiment of the CPE. They are the fossilized remains of these powerful rivers and vast temporary lakes. Perhaps the most famous example of this process is a historical fact you can go and see for yourself. The beautiful multicolored rock layers of the Chinle Formation, which paint the landscape of the American Southwest in shades of red, purple, and blue, were laid down by the rivers, swamps, and lakes of this exact period. And a quirky, beloved feature of this formation, the Petrified Forest National Park in Arizona, is a direct and stunning consequence of this watery chaos. The park's vast fields of colossal rainbow-colored stone logs are essentially the remains of a gigantic, ancient log jam. Imagine one of the new conifer forests, full of towering trees being undercut by a raging river during a flood. The trees are washed downstream, eventually collecting in a massive pile in a bend of the river, where they are buried by sediment and, over millions of years, are slowly replaced by minerals. The park is a fossilized traffic jam from one of the CPE's mega rivers. Scientists, specifically sedimentologists, can even reverse engineer these ancient rivers by studying the rocks they left behind. Through careful analysis of the size, shape, and type of pebbles found in the conglomerate layers, they can calculate the speed and power of the water that carried them. Larger, rounder pebbles mean a faster, more energetic river. It's a kind of geological forensics, allowing us to feel the power of a river that vanished 230 million years ago. But even with such clever techniques, deep questions remain. Geologists still argue over the extent to which pre-existing tectonic basins directed this new water flow versus the ability of the CPE's mega-rivers to carve new paths across the continent. Was the water simply following the path of least resistance in old valleys and fault lines, or was the deluge so immense that it ignored the old rules and sculpted a new landscape according to its own fluid logic? The green world is also a fluid one. The ground itself is no longer solid and dependable. It is temporary, a landscape in a constant state of being unmade and remade. The world is now a fluid, shifting landscape of mud and water, cloaked in a deep and permanent green. A world that changes its physical form this quickly is a dangerous and disorienting place to live. The old rules of survival no longer apply. So, what of the kings of the old world? What of the great Crurotarsan predators that you saw moving with such untouchable confidence in the dry twilight? How are they faring in this new, wet realm? Let's find our apex predator again, the mighty Postosuchus. You see it now, not swaggering across an open plain, but huddled miserably at the base of a towering, dripping conifer. Its magnificent, scaly hide is slick with a perpetual film of rainwater and mud. It looks cold, sluggish, out of place. The primary advantage it held in the old world has been turned into a crippling liability. As a large ectothermic, or cold-blooded reptile, it relied on the sun. It was a creature powered by external heat, using the blistering Triassic sun to warm its massive body, to fuel its powerful muscles, and to drive its metabolism. But the sun is gone. In this world of perpetual cloud cover and constant cooling rain, there is no place to bask, no way to properly warm up. The Postosuchus is living in a state of constant, debilitating chill. Its movements are slow and labored. Its speed and power, which were so devastating on the open, sun-baked plains, are now locked away behind a wall of thermal debt. The very climate has robbed the king of his strength. It is, to put it mildly, a very bad time to be a sunbather. And it's not just the temperature. The landscape itself has become an enemy. The long, open sight lines of the arid scrubland are gone, replaced by the tangled, claustrophobic gloom of the new forests. The hunting style of the Postosuchus, likely a combination of ambush and overwhelming charges across open ground, is now almost useless. How do you charge through a swamp? How do you ambush prey in a dense, misty forest where every sound is muffled by the dripping leaves and every scent is washed away by the rain? The world has become a maze, a puzzle that its powerful but specialized body is simply not equipped to solve. But the final, most devastating blow is the simplest one of all: hunger. The great herds of Dicynodonts and Rhynchosaurs, the vast walking larder that had sustained the Crurotarsan dynasty for millions of years, are in trouble. As we will see, their own food sources are vanishing, and they are struggling to adapt to the wet, alien world. The foundation of the food pyramid is crumbling, and for the predators at the very top, the collapse is catastrophic. A starving king is a king no longer. The story of this decline is written clearly in the fossil record. This is the scientific evidence that confirms our observations. In the rock layers just below the beginning of the CPE, fossils of large terrestrial Crurotarsans like Postosuchus are common and diverse. But as you move up into the grey, wet layers of the CPE itself, they become rarer and rarer. Species after species vanishes from the record. The rocks tell a quiet, clinical story of a dynasty in collapse. Of course, the story is not one of complete annihilation. Some Crurotarsans did survive. In fact, the historical fact is that the one lineage that would make it through, the crocodilomorphs, did so by going in the opposite direction. They abandoned the land and became ever more specialized for a life in the water. By becoming semi-aquatic, they found a niche that was insulated from the worst of the changes on land. They are the great survivors of their clan. And some of their land-based cousins may have found temporary reprieves. The quirky armored Archosaurs, those herbivorous Crurotarsans that looked like Triassic armadillos, might have actually done well for a time, using their spade-like snouts to dig for the abundant roots and tubers in the soft, wet soil. But for the great land predators, there was no escape. And so, paleontologists are left with a classic chicken and egg question. Was the decline of the Crurotarsans a direct result of the climate, or was it a secondary effect of the collapse of their herbivore food supply? This is a scholarly debate with no easy answer. The truth is most likely that it was a devastating feedback loop, a perfect storm of misfortune. The cool, wet climate weakened them. The new forested landscape hindered them, and the disappearance of their prey starved them. It was an inescapable trap. You watch the once mighty Postosuchus shivering in the endless rain. The king is being quietly, impersonally, and irreversibly dethroned by a change in the weather. The dethroned king, the Postosuchus, is starving because the foundation of its world is vanishing. To understand the predator's plight, we must first understand the tragedy of its prey. Let's turn our attention now to the great herbivore herds, and to one of the most successful and strangest of all Triassic creatures, the Rhynchosaurs. You find a small group of them, huddled in a clearing in the dark, dripping conifer forest. They look lost. These squat, powerful, beaked reptiles, which were so perfectly at home on the arid plains, now seem like refugees in an alien landscape. And here is the profound and terrible irony of their situation. They are standing in a world that is bursting with more green, more plant life than it has seen in millions of years, and they are starving to death. Their dilemma is a classic evolutionary tragedy. It is the specialist's trap. The Rhynchosaurs were masters of their environment, and the key to their mastery was their mouth. Their name, a quirky and simple label, says it all. Rhynchosaur just means beak lizard. Their entire existence was built around that powerful shearing beak and the bizarre, ever-growing tooth plates within their jaws. This was a highly advanced, precision piece of biological engineering, perfectly evolved to do one job: to dig up and slice through the tough, fibrous, low-lying plants that dominated the dry Triassic world. But that world, and those plants, are gone. The Rhynchosaurs are now expert locksmiths in a world with no locks. They are faced with a twofold problem from which there is no escape. First, the new menu is all wrong. The forest floor is carpeted with soft, watery ferns. While edible, these likely don't provide enough nutrition to sustain their large bodies, and their powerful shearing jaws are overkill, like using industrial cable cutters to slice a piece of fruit. The dominant plants, the towering conifers, are even worse. Their needles are resinous and tough, and their woody branches are too fibrous for the Rhynchosaur's slicing jaws to process effectively. The direct scientific evidence for their specialized diet is incredibly precise. By examining their fossilized tooth plates under an electron microscope, scientists can perform a microwear analysis. The microscopic scratches and pits left on the chewing surfaces act as a diary of the animal's last meals, and they show a pattern consistent with processing very specific, tough, and likely gritty plant material. They were not generalists, they were fussy eaters, and their favorite food has just been wiped off the face of the planet. The second problem is even more fundamental. Even if they could eat the nutritious needles of the new conifers, they can't reach them. A Rhynchosaur's body is built low to the ground, a perfect design for grazing on scrub and digging for roots. They have no way to rear up, no long neck to stretch. They are trapped on the forest floor, able to eat only what they can reach, or what happens to fall from the canopy above. They are living on the bottom floor of a skyscraper, starving while the pantry is on the top floor. To appreciate the scale of this collapse, you have to understand just how successful they were before the rain. This is a historical fact written in fossil beds around the world. In some pre-CPE fossil sites, particularly in what is now South America, Rhynchosaurs were overwhelmingly the most common large animal. Their fossils can make up 60% or more of all vertebrates found in those layers. They were the Triassic equivalent of the bison on the American plains, or the wildebeest on the Serengeti, the ubiquitous keystone herbivore. And now, they are fading away. The fossil record shows their decline to be swift and brutal. While some paleontologists propose that Rhynchosaurs might have survived longer in certain refuge areas where patches of the old flora clung on, the fossil evidence for their decline and extinction during the CPE is, for the most part, quite abrupt. They were a cornerstone of the old world, and when that world washed away, they were washed away with it. You watch the small, hungry herd, listlessly sniffing at the damp earth, and you realize you are watching a ghost. Their perfection was their doom. The Rhynchosaurs, for all their former glory, were just one half of the great herbivorous engine that powered the Triassic. The other half, the great dynasty of our own distant relatives, the Dicynodonts, faced the same green, watery apocalypse. And for them, the failure was not in their beaks, but in their bellies. You are watching a herd of placerias again, those tusked, barrel-chested creatures that seemed so robust and successful in the dry times. Now, in the perpetual dampness of the conifer forest, they look gaunt. Their skin, which should be taut over powerful muscles, hangs loosely. They move with a profound weariness. Like the Rhinchosaurs, they are adrift in an ocean of inedible green. Their problem is similar, but cruelly different. Their powerful turtle-like beaks were excellent for snipping the tough, low-lying flora of their old world. But they are useless for grinding down the woody, fibrous needles and branches of the new conifers that surround them. They too are trapped on the forest floor, unable to reach the canopy. They are trying to adapt, subsisting on the soft, watery ferns that are everywhere. But it's like trying to live on celery. There just isn't enough caloric content to power their large, active bodies. They are slowly, collectively, wasting away. The key to their failure lies in a simple trick they never learned. Many herbivorous animals, then and now, have a secret weapon for digesting tough plant matter. They use gastroliths, or stomach stones. They intentionally swallow pebbles and rocks, which are held in a muscular part of the stomach, a gizzard, that acts as a gastric mill. The stones tumble against each other, grinding the tough plant fibers into a digestible pulp. It's a beautifully simple and effective solution to the problem of eating wood. Early plant-eating dinosaurs were already doing it. But the Dicynodonts were not. The scientific evidence for this is a compelling case of absence. In the hundreds of exquisitely preserved Dicynodont fossils found around the world, some with even the contents of their gut intact, we have never found a pile of polished stomach stones. They simply didn't have this technology, and we have another, even more direct window into their diet, courtesy of what they left behind. We have their fossilized poop. Coprolites, as they are scientifically known, are a treasure trove of information. And analysis of Dicynodont coprolites from this time tells a sad story. They are packed with the spores of ferns, confirming that these creatures were trying to survive on the low-quality food of the forest floor. In stark contrast, coprolites from the early plant-eating dinosaurs living in the exact same time and place are found to contain up to 85% wood fragments. The proof is undeniable. The dinosaurs could eat the new forest. The Dicynodonts could not. And so, this great and ancient lineage, a group that had dominated the planet for 40 million years, is coming to an end. This is a historical fact of immense significance. The Dicynodonts were the ultimate survivors. They arose in the Permian, lived through the Great Dying, the most profound extinction event in Earth's history, and went on to conquer the globe. And now their story ends, not with a bang, but with a slow, quiet starvation in the endless rain. It's a poignant end for a group that was, right up until the very end, still capable of greatness. As a quirky testament to their enduring potential, one of the very last Dicynodonts known, a species from Poland named Lisowiczia bojani, was also the largest. It reached the size of a modern elephant, a final spectacular giant that lived right on the cusp of the group's total annihilation. You watch the tired herd of placerias and feel a strange sense of distant family grief. They were synapsids on the same great branch of the tree of life as us. Their failure is, in a way, our failure. Exactly why the Dicynodonts, such a resilient and long-lived group, failed to adapt to this crisis when they had survived so much before is a question that still fascinates paleontologists. Perhaps their long success had locked them into a strategy they could not change. Perhaps it was just bad luck. But whatever the reason, their time is over. The long and epic story of the tusked kings is drawing to its final, damp, and tragic close. The story of the Dicynodonts, our distant cousins, ends in the quiet mud of a rainy forest. It is a terrestrial tragedy. But this quiet apocalypse on land was not happening in isolation. It was mirrored by an equally devastating, though largely invisible, catastrophe beneath the waves. The sickness that had been creeping into the world's oceans has now become an acute crisis. We are leaving the dripping forests of Pangaea behind and sinking now down into the warm, murky waters of the Panthalassa Ocean. The scene below the surface is one of profound decay. The vibrant, colorful world of a healthy marine ecosystem is gone. In its place is a submarine graveyard. The water is thick with suspended silt, washed down from the tormented continent by the new mega rivers. Sunlight struggles to penetrate the gloom. And as you descend, you see that the seafloor in many places is coated in a thick, black, slimy ooze. This is the physical manifestation of anoxia, a lack of oxygen. This black ooze is organic matter that has fallen to the seafloor and has not fully decayed because the oxygen needed for that process is gone. The ocean floor is being embalmed. This is the peak of what scientists call the Carnian crisis. And in this suffocating, acidic, and overheated water, life is collapsing. The beautiful ammonites, those free-swimming relatives of squid with their ornate, spiraled shells, are suffering immense losses. The acidifying water makes it harder for them to build their shells, and species after species is blinking out of existence. The strange eel-like conodonts, which had been a fixture of the oceans for hundreds of millions of years, are nearly wiped out, pushed into an evolutionary corner from which they will never escape. And the reef builders are gone. The delicate stony corals have vanished completely. The very concept of a reef, a great living city in the sea, has been erased from the planet. The fossil record simply goes silent. For millions of years after this event, there will be no true reefs on Earth. The relentless rain on the land is making things exponentially worse for the sea. The immense new rivers are not just carrying water, they are carrying the continent itself. Trillions of tons of eroded soil, sediment, and nutrients are being washed into the coastal waters. This massive influx of nutrients triggers colossal blooms of algae, turning the surface of the sea into a thick, green soup. But this boom is short-lived. The algae quickly die, sink into the depths, and decay. This process of decay is a hungry one. It consumes all the available oxygen in the surrounding water, intensifying the anoxia and making the dead zones even larger and more deadly. The rain is not just drowning the land, it is actively suffocating the sea. This marine extinction event is a historical fact of such magnitude that it is used by geologists as a formal boundary marker in the geologic timescale. It is a punctuation point in the deep history of our planet. And yet, even in this devastation, life is endlessly opportunistic. A quirky detail from the aftermath shows this resilience. With the corals gone, a new and temporary kind of ecosystem appeared. Disaster reefs made entirely of bivalves. Hardy, tolerant shellfish, like ancient oysters and clams, took over the vacant space, their shells piling up over generations to create reef-like structures, a strange and short-lived monument to a global crisis. The scientific evidence for the triple threat of stressors is locked into the marine rocks. oxygen isotope data, gathered from the fossilized shells of the few creatures that survived, acts as a paleothermometer, showing a clear and dramatic spike in ocean temperatures. At the same time, specific geochemical markers and the presence of that black, laminated ooze in the sediments are unambiguous proof of widespread anoxia. This brings us back to the great, unresolved scholarly debate. The relative importance of the big three stressors, warming, acidification, and anoxia, in causing the marine extinction is a subject of ongoing research, with different factors likely dominating in different parts of the ocean. It was a multifaceted attack, a death by 1,000 cuts. The great dynasties of the land are falling apart, and the very foundations of life in the sea are crumbling. The world is being comprehensively, globally unmade. The world is drowning in a slow-motion catastrophe. On land and in the sea, the old dynasties, the rulers of the long, stable age of the Triassic, are crumbling. It is a story of universal decay, a global crisis from which it seems nothing can recover. But in every great extinction, amidst the wreckage and the ruin, there are opportunities. For every specialist that finds its world has vanished, there is a generalist, or an opportunist, or simply a creature with a lucky new trick that finds a world of possibility has just opened up. It is time to turn away from the dying and look to the survivors. It is time to revisit those small, unassuming underdogs you saw so briefly in the dry twilight, the dinosaurs. They are no longer quite so small, and they are certainly no longer so rare. As you walk through the damp, dripping conifer forests, you see them with increasing frequency. Specifically, you see the first great dynasty of plant-eating dinosaurs beginning their rise, the Prosauropods. A creature like Plateosaurus moves through the gloom. It is not yet a true giant like its Jurassic descendants, but it is large, perhaps 20 or 30 feet long. It can walk on 4 legs, but it can also rise up on its powerful hind legs, using its long, muscular tail as a counterbalance to reach high into the branches of the new trees. And most importantly, unlike the starving Dicynodonts and Rhynchosaurs, it looks healthy. It looks well-fed. This presents a puzzle. How can this be? The Dicynodonts and Rhynchosaurs, with their highly specialized beaks and tooth plates, are starving. How is this dinosaur, with its ridiculously simple peg-like teeth that seem only good for raking in leaves, thriving? The answer is a stroke of evolutionary genius, a solution that is both brilliantly effective and brutally simple. The answer is not in its mouth, but deep within its belly. As you watch the Plateosaurus, you see it lower its long neck not to a plant, but to the gravelly bank of a stream. It carefully, deliberately, swallows a few smooth, polished pebbles. This is the secret. This is the dinosaur's first great advantage. It has a secret weapon that the Dicynodonts lacked: a gastric mill. Like many of their living descendants, the birds, these dinosaurs, had a gizzard, a muscular, thick-walled section of their stomach. The stones it swallows, known as gastroliths, are stored there. And as the gizzard contracts, it tumbles these stones against each other, grinding the tough, fibrous conifer needles that the dinosaur has swallowed into a digestible pulp. It has, in essence, outsourced the act of chewing from its weak mouth to its powerful gut. It has a rock tumbler in its stomach. This simple adaptation changed everything. It was the key that unlocked a vast new food source. The endless conifer forests, which were an inedible green desert to the other herbivores, have become an all-you-can-eat buffet for the prosauropods. While their competitors waste away, the dinosaurs are feasting. The scientific evidence for this is definitive and fascinating. The most compelling proof comes from the discovery of several beautifully articulated dinosaur skeletons found with a distinct, neat pile of highly polished stones located right within their rib cages, exactly where a gizzard would be. It's the paleontological equivalent of being caught red-handed. This trick would become a historical fact of dinosaur life for the next 150 million years, used by everything from these early prosauropods to the colossal 80-ton sauropods of the Jurassic. It's a trick still used today by ostriches and chickens. But with this discovery comes a quirky little problem for paleontologists. Polished stones are often found loose in dinosaur-bearing rock layers, and it's tempting to call them all gastroliths. But without the context of a skeleton, it's impossible to be sure. These isolated stones are sometimes cheekily referred to as gastromyths. The origin of this brilliant adaptation is still a matter of some discussion. Whether the very first dinosaurs had gastroliths is uncertain, but it's clear that this adaptation was quickly adopted by the herbivorous lineages as they began to diversify. It was the perfect tool for a changing world. It was the innovation that allowed the first plant-eating dinosaurs to not just survive the crisis, but to actively profit from it. They are fueling their growth on the wreckage of the old world. They have found their engine. The dinosaurs have found their fuel. Their simple, ingenious gastric mill has turned the entire planet into a feast. But a powerful engine is useless without an equally powerful air intake system. Food provides the fuel, but the air provides the fire that burns it. And it is in the very act of breathing that the dinosaurs held their second and perhaps greatest advantage. It was a secret weapon hidden deep inside their chests, an adaptation that made them masters of a suffocating world. Let's turn our attention from the large, plant-eating prosauropods to their smaller, more active cousins, the theropods, the lineage of two-legged carnivores. You see one now, a creature like a coelophysis, darting through the misty undergrowth. It is a portrait of effortless agility and stamina. It can run, leap, and hunt for hours without tiring, while its competitors, the Crurotarsans and synapsids, would be left gasping. The reason for this lies in the very air you are breathing. Remember, this is a world choked with volcanic carbon dioxide, a heavy and potentially oxygen-poor atmosphere. For most animals, every breath is a labor, but not for the dinosaurs. Their respiratory system was a marvel of biological engineering, a design that is so efficient it feels almost alien compared to our own. Your lungs, and the lungs of all mammals, work like a set of bellows. You inhale, fresh air rushes in and mixes with the stale, leftover air from the previous breath. Oxygen is exchanged, and then you exhale. It's a two-way, dead-end system, and it is fundamentally inefficient. The dinosaurs evolved something far better. They had a one-way flow-through system, the very same system that allows their modern descendants, birds, to perform feats of incredible endurance. Here is how it worked. A series of air sacs, distributed throughout their torso and even extending into the hollow spaces of their bones, acted as holding chambers. When a dinosaur inhaled, the air was drawn into a rear air sac. When it exhaled, that fresh air was pushed from the sac through the lung. With the next breath, that now deoxygenated air was pushed out into a forward air sac and then expelled, while a new batch of fresh air entered the rear. It sounds complex, but the result is simple and revolutionary. A continuous, one-way stream of fresh, fully oxygenated air flowing across the lung surfaces, both on the inhale and the exhale. There was no mixing of fresh and stale air. they extracted oxygen with breathtaking efficiency. In the thin, difficult atmosphere of the CPE, this was a superpower. It gave them stamina that no other animal of their size could match. This advantage was further amplified by their upright, two-legged posture. A sprawling lizard, when it runs, bends its body from side to side, compressing one lung while expanding the other. Its breathing is fundamentally constrained by its movement. The dinosaurs' pillar-like legs, a design we saw was made possible by their open hip socket, unshackled their breathing from their locomotion. Their torso remained stable as they ran, allowing their hyper-efficient lungs to work at full capacity. The historical fact is that the skeletal evidence for this system has been known for over a century. The presence of hollow spaces and distinct openings, called pneumatic foramina, in the vertebrae of many dinosaurs. For a long time, these were just thought to be for weight saving. Now we know they were the docking points for the air sacs that powered this incredible breathing machine. The more definitive scientific evidence comes from modern technology. When paleontologists place these fossilized vertebrae into medical CT scanners, they can digitally reconstruct the intricate, honeycombed and hollow internal structures, revealing the complex plumbing that was a hallmark of their respiratory system. And if you want a quirky, modern-day example of this system's power, look to the birds. It is this dinosaurian inheritance that allows a tiny hummingbird to power its wings at 80 beats per second, a metabolic rate that would make a mammal explode. It is this system that allows the bar-headed goose to fly over the Himalayas, breathing air so thin it would render a human unconscious in minutes. And the origin of this superpower is still a matter of scientific excitement. Exactly how far back in the dinosaur family tree this advanced respiratory system goes is a hot topic. Did it appear at the base of Dinosauria, a feature of the very first dinosaur? Or did it evolve independently in the different major groups? The clues are still being pieced together. But one thing is certain. With a gut that could digest the inedible and lungs that could master the unbreathable, the dinosaurs were perfectly pre-adapted for the apocalypse. While the old world was starving and suffocating, they were breathing easy. With a gut that could turn the new world into fuel and lungs that could master the poisoned air, the dinosaurs had the keys to the kingdom. The old rulers were gone, the locks were broken, and the doors to the empty castle stood wide open. What followed was not just survival, it was conquest. The small, skittish creatures you saw hiding in the shadows of the old world are now stepping into the light, and in the crucible of this global crisis, they are being forged into new and varied forms. You are witnessing an explosion of life. The basic dinosaur body plan, that light, agile, radial bipedal frame with its efficient hips and lungs, proved to be an incredibly versatile blueprint. With the great Crurotarsan predators in decline and the vast herbivore herds of Dicynodonts and Wrangellian vanishing, the planet was suddenly full of job openings, and the dinosaurs, as the most qualified applicants, rushed to fill every vacant position. This is adaptive radiation in action, a single ancestral group rapidly diversifying to adapt to a wide range of new lifestyles and opportunities. You can now see the three great future clans of the dinosaur family tree beginning to diverge and establish their identities. First, there are the theropods, the beast-footed carnivores. Creatures like Coelophysis are now the dominant predators in many ecosystems. You see them not as lone hunters, but as packs of fast, intelligent, and lethal predators, their superior stamina allowing them to run down any of the struggling survivors of the old world. The reign of the sluggish Crurotarsan king is over. The age of the nimble theropod wolf pack has begun. Then there are the sauropodomorphs, the lizard-footed forms, the ancestors of the great long necks. The prosauropods you saw earlier, like Plateosaurus, are becoming larger and more numerous. They are now the planet's chief herbivores, using their height to browse on the high branches of conifers and their gastrolith-filled guts to digest them. They move with a newfound confidence through the forests, unchallenged by the ghosts of the old herbivores. And finally, you see the first hints of the third great clan, the Ornithischians, the bird-hipped dinosaurs, a group that would later produce the iconic stegosaurs, ankylosaurs, and the horned dinosaurs like Triceratops. They are still rare in this new world, but they are here. You might catch a glimpse of a creature like Scutellosaurus, a small, two-legged plant-eater no bigger than a large dog. What makes it remarkable is the strange armor beginning to sprout from its skin, hundreds of small, bony studs or scutes running along its back and sides. It's a quirky and almost comical-looking animal, a walking pincushion. But in those simple studs, you can see the first evolutionary experiment that will lead to the great plates of Stegosaurus and the impenetrable bony armor of Ankylosaurus. The scientific evidence for this explosion of life is clear in the fossil record. As paleontologists move from the rock layers of the pre-CPE world into the layers of the CPE and just after, they see two things happen. First, the sheer number and diversity of dinosaur species skyrockets. Second, and just as important, their morphological disparity increases dramatically. That's the scientific way of saying that their range of body shapes and sizes exploded. They weren't just making more of the same kind of dinosaur, they were rapidly evolving into big ones, small ones, carnivores, herbivores, and the first armored specialists. This period, the end of the Carnian and the following Norian age, is known as a historical fact in paleontology. It is the great dinosaur diversification event. But was it really an instantaneous explosion? Or was it something that was already happening, just waiting for a catalyst? This is a fascinating scholarly debate. Whether this diversification was a rapid explosion that happened because of the extinction, or a more drawn-out fuse that was already burning before the CPE is debated. But all agree the CPE threw gasoline on the fire. The dinosaurs may have already been primed for success, but the crisis cleared the board and allowed their expansion to happen at a pace that was, geologically speaking, almost instantaneous. The underdogs have won. The world has been reset, and the dinosaurs are its new operating system. The dinosaurs have inherited the Earth. Their twin advantages of a superior gut and superior lungs have allowed them to not just survive the global crisis, but to thrive within it, exploding into 100 new forms that have now claimed every vacant corner of the Pangaean landscape. But what was it actually like to live in this new kingdom they had won? What did it feel like, moment to moment, to be an animal born into the perpetual twilight of the Carnian Pluvial episode? Let us slow down and for a while simply exist in this strange grey and green world. The concept of a day has lost its meaning. There is no sunrise. The world simply transitions from a deep, profound, and rainy darkness to a slightly less dark, universally grey and rainy twilight. The morning does not break. It seeps in. The rain might soften from a steady downpour to a fine hanging mist, and the world resolves itself into a series of soft, blurry shapes. A herd of prosauropods moves like a fleet of ghosts through the immense, dripping fern prairies, their calls echoing strangely in the dense, damp air. Everything is slick with moisture. Every leaf holds a perfect, trembling drop of water. The deep green of the conifers and the rust brown of the fallen needles on the forest floor are dark, saturated, and rich. There are no bright colors here. As the day wears on, the light reaches its peak. But there is no sun, only a diffuse, shadowless, silver-white glare from behind the unbroken ceiling of cloud. This is as bright as it ever gets. In this flat, even light, the world feels claustrophobic and strangely intimate. The constant mist shortens the horizons, enclosing you in a small, personal bubble of existence. The only sounds are the sounds of water, the endless, gentle patter of rain on leaves, the gurgle of the ever-present streams, the soft squelch of your own feet in the mud. The air is thick with the smell of wet earth and pine resin, a clean, sharp scent mixed with the sweet, musty perfume of decay. This is the smell of a world that is constantly growing and constantly rotting, all at once. What would it be like to live your entire life, and for your species to live for countless generations in such a world? A dinosaur born during the CPE would have no concept of a shadow. It would have no instinct to seek shade from a sun it had never felt. It would never have seen the crisp, clear light of a dry morning, or the sharp, black canopy of a starry night. The moon would be a forgotten myth. The perpetual grey rain would not be an event or a type of weather. It would be the fundamental, unquestioned nature of reality itself. There is the feeling of never being truly dry, a constant, low-level dampness that seeps into everything. Life is lived in a state of permanent saturation. In a world without sun, the senses of sight would become less important. In the misty gloom of the deep forests, it would be the senses of smell and hearing that would dictate the terms of survival. An animal's world would be a tapestry of scents on the wet air, a landscape of sounds echoing through the dripping trees. It would also be a world without fire. Natural wildfires, a crucial engine of destruction and renewal in many ecosystems, would be impossible. The planetary cycle of fire has been temporarily extinguished, replaced by a planetary cycle of water. As the day ends, the silver light begins to fade back into a deep grey. The rain, which had softened to a drizzle, might pick up again, becoming a steady, hypnotic drumming on the canopy of the forest. The nocturnal creatures emerge into a world that is not much darker than the one they slept through. The air grows cooler, and the mist thickens in the low-lying areas, flowing like a slow, silent river between the great tree trunks. This is a world held in a state of suspended animation, a long, slow, 2-million-year-long afternoon. To put that time scale in perspective, imagine every moment of recorded human history, from the first Sumerian cities to the world you live in now, taking place under a single, unbroken, global rainstorm. That is the true scale of this perpetual twilight. It is not a season of crisis. It has become an entire age of the world. You are standing in the heart of a 2-million-year-long twilight, a world that seems locked in a single monotonous rainy moment. It feels eternal. It feels like the new and permanent state of the Earth. But nothing, not even a storm that spans geological ages, lasts forever. The planet is a complex, self-regulating system. It has feedback loops and safety valves that work on timescales almost too vast for us to comprehend. The very forces that were thrown into chaos to begin this crisis are now, slowly and silently, beginning to work towards its end. The fever is about to break. The planet is starting to heal itself, and it is doing so in two primary ways. The first is biological. Remember the vast, dark, and seemingly endless conifer forests that have conquered the globe? They are not just passive scenery. They are an active participant in the planet's recovery. They have become the green lungs of the Earth, and they are breathing in. With every moment that passes, the trillions upon trillions of leaves and needles are inhaling the very carbon dioxide that caused this crisis, using it to build their wood, their roots, and their resin. When these giant trees die, they fall into the swampy, waterlogged ground. In this oxygen-poor environment, they do not fully rot. Instead, they are slowly buried, locking all the carbon they contain away in what will one day become the great coal seams of the future. The biological world, in response to the crisis, has created a colossal carbon capture machine. The second mechanism is geological, and it is even more powerful. It is a process that begins with a single drop of rain. The rainwater falling through the CO2-rich atmosphere has become a weak carbonic acid. As this acid rain falls on the land, it chemically reacts with the rocks. It dissolves them. This process of chemical weathering is a historical fact of planetary science. The weathering of silicate rocks is one of Earth's primary, long-term mechanisms for regulating atmospheric CO2. It is, in essence, the planet using the rain to scrub its own atmosphere. This reaction pulls CO2 out of the air and converts it into dissolved bicarbonates in the water. These bicarbonates are then carried by the new mega-rivers on their journey to the sea. Once in the ocean, this is where the magic happens. Tiny marine organisms like plankton absorb these bicarbonates from the seawater and use them to build their microscopic, intricate shells of calcium carbonate. When these creatures die, their shells rain down into the deep, dark silence of the ocean floor. Over thousands and millions of years, these layers of shells are compressed into rock. They become limestone. This is the planet's ultimate carbon sequestration solution. It has taken the carbon that was once a poison in the air, and it has locked it away in the geological library of the Earth's crust, where it will remain for hundreds of millions of years. The scientific evidence for this is clear. In marine sediments laid down after the peak of the CPE, the layers of limestone and other carbonate rocks become dramatically thicker, indicating the ocean was successfully burying the excess carbon. Some scientists refer to this entire process with a wonderfully quirky and apt name: the geological thermostat. It is the Earth's natural system for regulating its own temperature. When the planet gets too hot, the weathering processes speed up, pulling more CO2 out of the air and cooling the planet back down. It works perfectly. The only catch is that its response time is measured in millions of years. And of course, there is one final crucial factor. Far to the north, the Wrangellian eruptions, the great engine of this catastrophe, are finally, after 5 million years of fire, beginning to sputter and die down. The input of new CO2 is dwindling to a trickle. And so, a great scholarly debate continues among scientists. What was the primary driver of the recovery? The relative importance of the biological pump, the forests, versus the geological pump, the rock weathering in drawing down CO2 after the CPE, is a key area of modeling and research. Was it the trees or the rocks that did the most work? The truth is that they were both working together, a planetary tag team fighting the fever. And now, you can feel the first effects of their work. The rain, after an unimaginable eternity, is beginning to soften. The downpours are less frequent. The endless drizzle seems thinner, less substantial. The deep, oppressive grey of the sky seems, for the first time in 1,000,000 years, to be getting just a little bit brighter. The great planetary fever has broken, and the long, slow convalescence begins. The change is not abrupt. It is a process as slow as the one that began it. You are standing in a world where the rain has been the only constant for 100,000 generations, and now that constant is beginning to fail. The centuries slip by like a slow turning page. The relentless year-round downpours give way to seasons of slightly less relentless downpours. The endless drizzle is replaced by long periods of thick, hanging mist and fog. The soundscape of the world is changing. The constant hypnotic drumming of water on the forest canopy begins to falter, and in its place, for the first time, you can hear the sound of individual drops falling from the high branches, echoing in a world that is growing quieter. Another 1,000 years pass. There are now days, even weeks, with no rain at all. The world exists in a state of profound, dripping stillness, wrapped in a thick, white blanket of cloud that still hides the sky. The ground is still a sodden mire, and the air is still thick with moisture. But the active falling water is gone. The animals, the dinosaurs whose ancestors were born in the heart of the storm, have known nothing but this grey, wet, shadowless world. This is their normal. They are perfectly adapted to the dim light and the damp earth. And then, one day, something new happens. A wind begins to stir. Not the violent gust of a thunderstorm, but a steady, powerful, high-altitude wind. It is the breath of a changing world, the sign of new weather patterns forming in a healing atmosphere. You look up at the bottom of the cloud layer, and you see it beginning to move, to shred, to tear. At first, it is just a subtle thinning, a place where the grey becomes a brighter, purer white. Then a hole appears, a small, brilliant, and shocking patch of the deepest blue you can possibly imagine. And through that hole, for the first time in 2,000,000 years, a beam of direct, unfiltered sunlight strikes the earth. It hits the floor of the conifer forest like a spotlight, a column of brilliant golden light full of dancing dust motes. The effect is instantaneous and profound. The wet, dark green leaves of the ferns it touches are suddenly illuminated in a vibrant, impossible emerald. The dark, damp bark of the trees glows with a warm, reddish light. Everything it touches is revealed in a depth of color and clarity that has been absent from the world for an entire geological age. The animals are thrown into a state of utter confusion. A young prosauropod, which has wandered into the beam of light, is terrified. Its own shadow, a sharp, black, and utterly alien shape, has appeared on the ground beside it. It has never seen such a thing. It stomps and turns, trying to face the dark phantom that mimics its every move. Other creatures are simply blinded. Their eyes, adapted to a lifetime of perpetual twilight, are overwhelmed by the sheer intensity of the light. They turn away, blinking in pain and confusion at the sudden, inexplicable glare. Then the wind picks up, and the hole in the clouds widens. More and more sunlight floods the landscape. The entire forest, which was once a muted tapestry of greens and browns, is now a sparkling, glittering wonderland. Every leaf, every needle, every blade of grass holds a drop of water that now shines like a diamond. And a new sound begins to fill the air, a soft, universal hiss. The damp earth, the wet logs, the drenched foliage, all begin to steam as the warmth of the sun touches them. A gentle swirling mist rises from the ground, catching the new light in ethereal, swirling patterns. You can feel it on your own skin, a sensation that no living creature here has ever felt. The gentle, penetrating warmth of a sunbeam. The age of the perpetual twilight is over. The great rain has ended. The sun has returned to a world that has all but forgotten it. But the world it shines upon is not the same one it left behind 2 million years ago. It is a planet remade, resculpted, and repopulated. It is now, and for the foreseeable future, the world of the dinosaurs. That first glorious sunrise is not a singular event. It is the beginning of a new reality, the herald of another great climatic shift. The return of the sun signals the return of the old Pangaean climate engine. With the thick, insulating blanket of carbon dioxide now thinning in the atmosphere, the planet can once again radiate its heat out into space. The great global fever has passed, and the world is cooling. As it cools, the old, stable weather patterns, dictated by the sheer size of the supercontinent, begin to reassert their dominance. The mighty supercharged water cycle weakens. The Mega-Monsoon system retreats back to the coasts. The rain shadow, that great invisible wall that had kept the interior of Pangaea so dry for so long, slowly drifts back into place. The world is beginning to dry out, but it is not returning to the world it was before. The 2-million-year reign was not a dream that the world could simply wake up from. It was a geological and biological force of such magnitude that it has permanently altered the face of the planet. The landscape the dinosaurs have inherited is a hybrid, a world bearing the deep and lasting scars of the Great Flood. The historical fact is that the geological ages that follow this crisis, the Norian and the Rhaetian, are characterized by a widespread return to arid conditions, but it is an aridity of a completely new kind. The most significant change is the persistence of the great forests. The vast conifer groves, born in the endless rain, are now a permanent feature of the landscape. But they must now contend with long, dry seasons and a dwindling supply of water. They are no longer temperate rainforests. They are becoming something new, something more like the dry, seasonal woodlands of a modern Mediterranean climate. And with this new combination of dryness and immense forests comes a new and powerful ecological force: fire. A quirky but fascinating detail is that many of the conifer families that dominated this post-CPE world, like the ancestors of modern cypresses and redwoods, are fire-adapted. Their thick bark and resinous wood suggest that the new, drier forests were frequently swept by colossal wildfires, a dramatic and violent feature that was impossible during the long damp. The world's water is in retreat. The mighty mega-rivers that had carved the continent are now shrinking, their power draining away. They dwindle from year-round torrents into seasonal streams, leaving behind the gigantic, oversized canyons, valleys, and badlands they had scoured from the rock. The landscape is a testament to the flood, a world full of dry riverbeds that are far too large for the trickles of water that now flow within them. The vast inland lakes that had dotted the continent are evaporating under the returning sun, shrinking year by year, leaving behind immense, glittering white pans of salt and gypsum, evaporite deposits that signal the triumphant return of aridity. The story of this great climate flip is told perfectly in the layers of rock. This is the ultimate scientific evidence. Geologists can see the grey, water-lane mudstones and conglomerates of the Carnian Pluvial episode come to an end, and directly on top of them, they find a new sequence of rocks, red, wind-blown sandstones from returning deserts, and the white chemical layers of the evaporites from the dying lakes. The sequence of rocks under your feet reads like a book. Dry, wet, dry. It is the entire story of the crisis, written in stone. Of course, this drying process was likely not a simple, uniform event. How quickly the world returned to full aridity is debated. Some areas may have remained relatively wet for millions of years, acting as refugees. Perhaps deep, spring-fed canyons or coastal plains sheltered pockets of the old rainforest ecosystem long after the surrounding lands had turned back to dust. It was likely a complex mosaic of different environments. This is the new stage upon which the age of dinosaurs will truly begin. A world of dry seasons and wet seasons. A world of vast, flammable forests and deep, winding canyons. It is a world defined and shaped, for all time to come, by the memory of a storm that lasted for 2 million years. The new sun shines down on a new world. It is a world of dry, fire-prone forests, a world of deep, silent canyons, and a world now dominated by the children of the storm. But this new world is haunted. It is a ghost kingdom, built on the foundations of a reality that has utterly and completely vanished. As you stand on a ridge, looking out over a vast, sun-drenched valley, the most profound feature of the landscape is not what is there, but what is not. The silence is the silence of absence. The emptiness is the emptiness of extinction. Where are the great herds? Where are the barrel-chested, tusked Dicynodonts that should be moving in their hundreds across this plain, their tough beaks snipping at the vegetation? They are gone. Where are the flocks of low-slung, powerful Rhinchosaurs, the great lawn mowers of the Triassic? They are gone. And where is the great predator, the swaggering Crurotarsan king, who should be stalking these herds from the shadows of the forest edge? It, too, is gone. The architects of the great Triassic ecosystem, the dynasties that had ruled the land for 40 million years, have been erased. Their reign, which must have felt so permanent, so unassailable, was washed away by the long rain. This was not a simple changing of the guard. It was the near-total collapse of multiple, magnificent lineages of life. The Crurotarsans, those masters of the hot, dry world, were chilled, starved, and left behind by a climate that no longer favored them. The Rhinchosaurs, the ultimate specialists, were a perfect solution for a world that no longer existed, their hyper-efficient beaks rendered useless by a change on the menu. And the Dicynodonts, our resilient and resourceful distant cousins, the great survivors of the Permian apocalypse, had finally met a crisis they could not outlast. Their story, a tale of tenacity that stretched back to before the first dinosaur even existed, has come to its final, quiet end. But is extinction always a final, absolute line? The fossil record is a story told with missing pages, and sometimes it contains miracles. Paleontologists have a beautiful name for creatures that seem to perform the impossible. They are called Lazarus taxa. Named after the biblical figure who was raised from the dead, a Lazarus taxon is a species or group that vanishes from the fossil record, is presumed extinct, and then mysteriously reappears in rock layers that are millions of years younger. This, of course, is not a true resurrection. It is evidence that a tiny, struggling ghost lineage must have survived the crisis, hiding out in some undiscovered refuge, too rare to leave a fossil. This population clung to life in the shadows for an age, before finally recovering enough to expand and appear in the fossil record once more. And so, a scholarly debate continues. Was the extinction of certain Triassic groups truly absolute? Or did a few ghost lineages persist unseen? The scientific evidence, which is the stark absence of their fossils in post-Carnian rocks, strongly suggests that, for the Wrangellian and the Dicynodonts, the end was final. There were no Lazarus moments for them. Their kingdoms were gone for good. This is the true legacy of the Carnian Pluvial episode. It was a great filter. It was a planetary reset button. The complex, stable world of the Middle Triassic, with its intricate food webs and its long-established rulers, was not just defeated, it was dismantled. The extinction of these creatures marks the end of an entire chapter in the history of life. The final closing moments of the age when crocodile cousins were kings and our own distant relatives were the most abundant large animals on Earth. You look out across the silent valley, and you can almost see the ghosts of the fallen, the faint, shimmering outlines of the herds that should be there. The new world is beautiful in the clear, dry sunlight, but it is a world built on graves. The Ghost Kingdom is silent, a world of memory and absence. But nature does not permit a vacuum for long. The great ecological stage, swept clean by the storm, is now ready for a new cast of actors. And as you look out over the sun-drenched, drying world, you see them. The inheritors are everywhere. The niches left vacant by the fallen dynasties have been claimed, and the age of dinosaurs has begun in earnest. You watch a herd of prosauropods, the ancestors of the great sauropods, moving through a grove of fire-adapted conifers. They are larger now than the ones you saw in the heart of the storm. Some, like Plateosaurus, can rise up on their hind legs to reach 30 feet into the canopy, their long necks allowing them to browse on a food source that was inaccessible to the squat herbivores of the Old World. They move with the unhurried confidence of creatures that have no predators to fear. They have taken the role of the Dicynodonts, and they are performing it on a grander scale. They are the new prime movers of the terrestrial ecosystem, their immense appetites shaping the evolution of the forests themselves. Down in the great, oversized canyon, carved by a now seasonal river, you see the new predators. A pack of sleek, fast theropods, creatures like Coelophysis, are picking their way along the gravel banks. They move with a sharp, intelligent alertness, their heads darting back and forth. They are not the lumbering, solitary bruisers that the Crurotarsans were. They are agile, cooperative hunters, a pack of desert wolves in a reptilian guise. They are the new apex predators, not by virtue of overwhelming size, but through speed, stamina, and numbers. The fossil evidence for their pack behavior is compelling, with places like Ghost Ranch in New Mexico yielding bone beds containing thousands of individuals, a snapshot of a vast social group that met a sudden end. They own this new world, from the riverbanks to the forest floor. This is the new reality. The sights and sounds of the planet have changed. The heavy tread of a Dicynodont herd is gone, replaced by the ground-shaking footfalls of the prosauropods. The intimidating roar of a Postosuchus has been replaced by the high-pitched calls of a pack of hunting theropods. The dinosaurs are no longer the marginal, skittish creatures you first met. They are the landscape. And here, in this new dinosaur-dominated world, we must pause and understand the true meaning of their victory. Their story is not a heroic epic of a long, drawn-out war where a superior group slowly and steadily outcompeted their rivals into extinction. The scientific consensus is clear on this. The dinosaurs did not win by being better in a direct, competitive sense. They won by default. The Carnian Pluvial episode was a global reset, a catastrophic event that so fundamentally changed the rules of life that the old, successful strategies of the Crurotarsans and synapsids were rendered obsolete overnight. The dinosaurs simply happened to possess a suite of lucky pre-adaptations. Their efficient lungs, their versatile guts, their upright posture, that made them uniquely suited to thrive in the chaotic aftermath. They did not conquer the old world. They were simply the only ones left to inherit the new one after the flood had receded. Their reign was not earned through battle. It was an inheritance bequeathed to them by a planetary catastrophe. They are the children of the storm, the accidental kings of a world reborn from chaos. The dinosaurs own the world. They have inherited the Earth not through a slow, grinding war of attrition, but in a sudden, catastrophic lottery. They were simply holding the winning ticket when the world changed. As you stand in this new, dry, post-diluvian world, watching the prosauropods browse and the theropods hunt, it feels like the story has reached its end. It feels like a new stability has been achieved. But the planet is not done yet. The Triassic period itself, the first great chapter in the age of reptiles, is drawing to its own violent close. The dynasty of the dinosaurs is only just beginning. Look at the inheritors around you, and in them, see the ghosts of a far more spectacular future. Watch the Plateosaurus as it rears up to strip needles from a high branch. Look at its solid limbs, its long, powerful neck, and the sheer, growing bulk of its body. You are looking at a blueprint. This 30-foot creature is just a few evolutionary steps away from the true titans of the Jurassic. Within this body plan is the potential for the 80-ton Brachiosaurus, a creature so vast it would shake the ground with every step, its head soaring as high as a 4-story building. Now, watch the sleek, fast-moving Coelophyes as it darts through the undergrowth. Its light bones, sharp teeth, and keen senses are the foundation for another, more terrifying dynasty. In its agile frame, you can see the potential for the great carnivores of the Jurassic, the fearsome Allosaurus. And further down that same line, you can see the faint, terrible promise of the ultimate predator, the 100-million-year-long culmination of the theropod story. Tyrannosaurus rex. Even in the quirky, armored hide of the little Scutellosaurus, you can see the seed that will blossom into the magnificent plates of Stegosaurus and the impenetrable shield of Ankylosaurus. The future is written in these Triassic survivors. But to unlock that future, they will have to endure one last trial by fire. The Triassic period will not end quietly. Another, even more violent spasm of planetary volcanism is on the horizon. This time, the culprit is the Central Atlantic Magmatic Province, or CAMP, a colossal large igneous province that will erupt as the supercontinent of Pangaea itself begins to tear apart, heralding the birth of the Atlantic Ocean. The very volcanoes that will cause the next great extinction are also the birth pangs of the modern world. This event will trigger the Triassic-Jurassic mass extinction, an apocalypse that will wipe out many of the remaining Triassic survivors. The last of the great Crurotarsans, the strange aquatic reptiles, and countless other groups. And yet again, the dinosaurs will sail through the storm. Exactly why the dinosaurs survived this second great extinction so well while their closest Archosaur relatives were devastated, still a topic of intense scholarly debate. Perhaps their hyper-efficient respiratory system gave them a decisive advantage in the poisoned, low-oxygen atmosphere. Perhaps it was a higher metabolism, or simply a case of being in the right place at the right time. Whatever the reason, they proved once again to be the ultimate disaster specialists. This final extinction event cleared the board completely. It wiped out their last remaining rivals, leaving the planet entirely, utterly theirs for the taking. This is the ultimate lesson of the long reign. The foundations of the legendary age of dinosaurs, the world of Jurassic giants that has so captivated the human imagination, were not laid on the sun-drenched plains of the Jurassic. They were forged in the darkness and the damp, in the mud and the mist of the Carnian Pluvial episode. That great storm was the crucible that tested all life on Earth, and it was the dinosaurs that emerged from it, hardened and honed, with the tools they needed to survive and thrive. The long reign gave them their first crucial inheritance. The fire at the end of the Triassic simply burned away the last of the other contenders for the throne. The dawn of the Jurassic is coming, and with it, the true dawn of a dynasty. The dynasty has its dawn, and the great Jurassic giants are waiting in the wings of the future. The story of the dinosaurs' rise to power is now cemented in the rock and the soil. But to truly appreciate the sheer planetary scale of the world they have inherited, we must leave the ground behind. We need a higher perspective. And there is another group of survivors from this age of crisis that can grant us that view. They are not dinosaurs, but they are their closest cousins, the pterosaurs. They were the first vertebrates in the history of life to achieve true powered flight, a historical fact of immense evolutionary significance. Long before the first bird, these remarkable reptiles had conquered the air, and like the dinosaurs, they had weathered the storm of the Carnian Pluvial episode and the final extinction at the end of the Triassic. Their ability to fly gave them the ultimate advantage, allowing them to transcend the chaos on the ground, to find food in isolated pockets, and to travel vast distances across the changing landscape. Imagine one now, an early form like Eudimorphodon. It is not a bird, nor is it a bat. It is something entirely different. Its long, slender wings are not made of feathers, but of a tough, leathery membrane of skin, stretched between its body and a single, impossibly elongated fourth finger. Its body is not covered in scales, but in a soft, fur-like covering of filaments called pycnofibers. The scientific evidence for this covering, preserved as faint impressions in stone, tells us that these were likely active, warm-blooded creatures, a far cry from the sluggish reptiles of the old world. We are rising now, lifting off from a high cliffside, catching a thermal updraft into the cool, dry air of the new era. The world unrolls beneath you like a map, and from this vantage point, the true legacy of the 2-million-year reign becomes breathtakingly clear. You see the vast, unbroken sea of dark green, the colossal conifer forest that stretches from one horizon to the other, a living monument to the great wet. But scarring this green carpet are the pale, winding ghosts of the flood. You can see the immense, dried-out riverbeds, some of them miles wide, snaking across the continent. From the ground, they are just canyons and badlands. But from up here, you can read them for what they are, the marks left by the arteries of a drowned world. You soar higher, and you see where the great forest frays at the edges, giving way to the returning red sands of the Pangaean desert. The world is a mosaic of biomes, a patchwork quilt of green forest, red desert, and the pale scars of the dead rivers. And from this great height, you can see the new life that animates it. Far below, a disturbance in the canopy of the trees marks the slow, inexorable passage of a herd of prosauropods. They are so large that they are like a slow-moving river of life within the forest. Further to the west, you see a puff of dust rising from the plains, a sign of frantic movement that can only be a pack of theropods on the hunt. There is a scholarly debate among paleontologists about how these creatures moved on the ground. Were they clumsy, shuffling walkers, or could they, as evidence now suggests, fold their wings neatly and walk with a surprisingly nimble gait on all fours? But up here, in the air, there is no debate. They are masters of the sky. This pterosaur's eye view confirms the totality of the change. This is not a world with a few new creatures in it. This is a new world from the ground up. The global re-landscaping project of the CPE is complete. The stage has been rebuilt, and it is now entirely, unquestionably, the property of the dinosaurs and their soaring cousins. The view from the pterosaur's wing shows a world remade, a planet that now belongs entirely to the dinosaurs. They command the day. They command the land. Their dynasty is absolute. But in the shadows of this new empire, hiding in the leaf litter of the forest floor, another group of survivors is quietly biding its time. They are the great inheritors of the future, but their inheritance is still 150 million years away. What about them? What about our own ancestors? As the Triassic gives way to the Jurassic, the first true mammalia forms are beginning to appear. Let's leave the soaring pterosaur and shrink our perspective down to the level of the moss and the fallen needles. Here, in the deep, damp darkness of the forest at night, a different kind of life emerges. You see a tiny creature, no bigger than a mouse, darting out from beneath the root of a giant conifer. It is covered in a coat of thick fur, its nose twitches constantly, and its long whiskers brush against the ground, tasting and feeling the world around it. This is a creature like Morganucodon, one of our earliest relatives, and its entire existence is a masterclass in survival through obscurity. The great crisis of the late Triassic, both the long reign of the Carnian and the final fire of the Triassic-Jurassic extinction, were primarily disasters for large, specialized animals. But for a tiny creature that already lived in the margins, the world didn't change that much. These early mammals were already experts at living in the cracks. They were nocturnal, a lifestyle that kept them safe from the day-patrolling dinosaurs. The scientific evidence from their fossils supports this. Their large eye sockets suggest eyes adapted for low light, and their greatly expanded nasal cavities point to a life dominated by a sophisticated sense of smell. They were creatures of a world of scent and shadow. They likely ate insects, worms, and whatever other small prey they could catch, a food source that was not as profoundly affected as the great herbivore herds. They survived the apocalypse because, in a way, they were already living in a world apart. But their survival came at a price. The very success of the dinosaurs, a success born from the fluke of the Carnian reign, now locked our own ancestors into this marginal existence. For the next 150 million years, the dinosaurs would so completely dominate every medium and large animal niche on the planet that there was simply no evolutionary room for mammals to grow. This was the great, long night of the mammals. While the dinosaurs evolved into the most spectacular and diverse giants the world has ever known, our family remained in the shadows as small, scurrying, nocturnal creatures. There is a scholarly debate about just how mammalian these first forms were. Had they evolved live birth, Or were they still laying eggs like their cynodont ancestors and the modern platypus? The fossil evidence is scarce, but it's clear they were living a life of frantic, high-energy survival. This is the great irony of our own story. We are here today because our ancient relatives, the Dicynodonts, failed. Their extinction during the CPE was part of the Great Reset that allowed the dinosaurs their chance. And we are here today because our other ancient relatives, the first true mammals, succeeded in the most humble way possible, by staying small, staying hidden, and waiting. You watch the tiny, furry creature as it snatches a beetle and scurries back into the darkness. It is a sleepy survivor, a creature of the deep night. And it will wait. It will wait through the entire age of Jurassic Titans, through the long drama of the Cretaceous, waiting for another cosmic catastrophe, another reset button that will finally clear the stage and give the children of the night their own chance to inherit the Earth. The tiny mammal vanishes back into the Triassic undergrowth, its long wait just beginning. Its story will be picked up again in 150 million years, after another, even greater catastrophe. But the legacy of the Great Rain did not go into hiding. Its consequences did not lie dormant. Its echoes are all around you, woven into the very fabric of the world you will wake up to tomorrow. This is not just a story about the deep past. It is the backstory of your own modern world. The next time you walk through a forest of pines or firs or giant redwoods, take a deep breath. That sharp, clean, resinous scent is an echo of the Carnian rain. The great conifer dynasties that dominate so many of the world's ecosystems today, from the boreal forests of the north to the temperate woodlands of the south, are the direct descendants of the trees that inherited the Earth during that long, wet crisis. The CPE was the event that cleared the board of their ancient floral rivals and gave them a warm, CO2-rich and waterlogged planet in which to thrive and diversify. The quirky monkey puzzle tree, or Araucaria, that you might see in a park or garden, is a living fossil, a direct link to the very forests that the first prosauropods browsed upon. The world's great forests are a living monument to the storm. The echoes are not just in the plants, but in the animals you see every day. Look out your window tomorrow morning at a sparrow on a wire or a pigeon strutting through a park. That creature is not like a dinosaur. It is a dinosaur. Birds are the last surviving branch of the theropod lineage, the direct descendants of the same group of agile carnivores that rose to power in the chaos of the CPE. The scientific evidence for this is now overwhelming, found in 100 shared anatomical details, from a fused wishbone to the very structure of their bones. And the superpowers that allowed their ancestors to conquer the Triassic are still with them. The hyper-efficient one-way respiratory system that allowed their ancestors to master the poisoned Triassic air is the very same system that allows a goose to fly over the Himalayas today. Their hollow bones are a direct inheritance. Even their simple behaviors are a ghost of their deep past. When a chicken swallows grit to help grind its food, it is echoing the ancient gastrolith strategy that gave the first herbivorous dinosaurs their crucial advantage. Every bird you see is a tiny, feathered time capsule, a living, breathing testament to the resilience of a dynasty that was forged in a 2-million-year-long storm. While scientists still debate which specific group of small, feathered theropods gave rise to the first true birds, that ancestral link is now beyond any reasonable doubt. The consequences are everywhere. The Great Rain was a crucible that accelerated evolution. It was a filter that rewarded innovation and punished over-specialization. It cleared the way for the dinosaurs, but also for the ancestors of modern lizards, turtles, and the crocodilomorphs that survived in the rivers. It was a foundational event. The world we inhabit is a direct, downstream consequence of the events that took place in that long, dark, and rainy chapter of the Earth's past. The story is not sealed away in the rock. It is alive, in the scent of the pine trees and the flutter of a sparrow's wings. The echoes of the rain are all around you, in the trees and in the birds. The story is written into the DNA of the modern world. But it is worth reflecting, in these final, quiet moments, on the kind of story this truly is. Because the rise of the dinosaurs and the shape of the world that followed is not a story of destiny. It is not the tale of a superior group marching inevitably towards their preordained glory. It is a story of pure, beautiful, and terrifying chance. It is a story of a contingent world. The history of life is not a straight, predictable road. It is a branching, chaotic river, and its course is changed forever by random, unpredictable events. Paleontologists and historians of science still debate the relative roles of predictable adaptation versus sheer dumb luck in shaping the grand course of life's story. But the tale of the Carnian rain is perhaps the greatest evidence for the power of luck. So let's ask the great what-if question. What if that specific patch of the Earth's crust, the one that would become Wrangellia, had remained stable? What if those fissures had never opened? What if the great volcanoes had never breathed their fire into the sky? What if it had never rained? In that alternate world, the world without the storm, the stable, arid climate of the Middle Triassic would have simply continued. The great Crurotarsan predators, the mighty Postosuchus and its kin, would have likely continued their successful reign as the planet's apex carnivores. The vast, placid herds of Dicynodonts, our tough and resilient cousins, would have continued to thrive, their dynasty unbroken. The Wrangellians would have continued to shear their favorite plants with their specialized beaks. It would have been a world of profound stability, the slow continuation of a drama that had already been running for tens of millions of years. And the dinosaurs? In that world, they would have almost certainly remained what they were: small, marginal, and rare creatures living in the shadows, a minor footnote in the grand story of the Triassic. There would have been no great extinction of their competitors, no empty world for them to inherit, no sudden evolutionary explosion. They would have been, at best, a quirky side project of evolution. And here is the stunning consequence of that thought experiment. In a world without the Great Rain, there would have been no Brachiosaurus. There would have been no Stegosaurus. There would have been no Triceratops and no Allosaurus. And there would have been no Tyrannosaurus Rex. The entire iconic, spectacular age of dinosaurs, the single most famous and awe-inspiring chapter in the history of life on Earth, was not an inevitability. It was an accident. Its existence is entirely contingent on a single, catastrophic, 2-million-year-long weather event. The fossil record, with its abrupt cutoff of the old fauna and the sudden radiation of the dinosaurs, is the hard scientific evidence for this chaotic, contingent model of history. The Great Storm was the pivot point upon which the entire future of terrestrial life turned. Its legacy is not just the forests and the birds we see today, but the very existence of the creatures that have so thoroughly captured our collective imagination. The most famous monsters that have ever walked the earth owe their very existence, their entire 150-million-year reign, to a fluke of geology and a quirk of the climate. It is a profound and humbling thought, a reminder that the story of life is more fragile, more unpredictable, and in many ways more beautiful than any planned and predictable epic. The dice were rolled, the storm came, the storm passed, and the world was spun onto a new and unpredictable path. And so our long journey through this forgotten chapter of Earth's history is coming to its end. Let us take one last quiet look at the world that the rain created. You are sitting on a warm, sun-drenched rock at the edge of a great canyon. The air is dry and clear. Far below, a small, gentle river, the great-great-grandchild of a forgotten torrent, snakes its way through the rust-colored landscape. The time of chaos is over. The frantic, explosive diversification of the dinosaurs has now settled into the slow, majestic rhythm of a stable ecosystem. The planet, after its long fever and violent recovery, is finally at peace. Life has adapted to the new normal. The survivors have established their kingdoms, and the world has found its new equilibrium. High above, in the brilliant blue sky, a pterosaur glides on the warm thermals, its shadow a fleeting darkness on the forest canopy below. In the distance, a large prosauropod, its belly full of conifer needles, has found a clearing and is sleeping in the afternoon sun, its great chest rising and falling in a slow, deep rhythm. The world is quiet now. The violence of the past has faded into the deep memory of the rock itself. There is still a debate among paleontologists about the speed of this recovery, whether the new ecosystems stabilized quickly, or if there was a long, chaotic interval that lasted for millions of years. But from here, in the early dawn of the Jurassic, it looks like a world that has found its footing. The planet is healed, but it is not the same. It is a world forever changed, a world that wears the memory of the storm in its very bones. The forests, the canyons, the deserts, and the very animals that populate them are all the children of that ancient crisis. The old world of the Triassic is a ghost kingdom, a story that is now told only by the silent absence of its players in the fossil record. And so, it is time for us to leave this place. Let the strange, unfamiliar constellations of the Jurassic sky, with their alien patterns and their cold, distant light, begin to fade from your mind. Let the faint, chittering call of a nocturnal Triassic insect, a sound no human was ever meant to hear, fall back into silence. Let the feeling of the warm, dry air on your skin and the scent of the resinous pine trees dissolve into the quiet of your own room. The long journey is over. The story has been told. And all that is left now is the profound and peaceful silence that follows a great and epic tale. The great, sleeping earth holds these stories deep within its stony heart, a library of worlds that have been lost to the immense, deep quiet of geological time. Tonight, you have walked through one of its most dramatic and forgotten chapters, a world of fire and flood that gave birth to the most magnificent creatures that have ever lived. But now the images of that ancient world can begin to soften, to blur at the edges, their vibrant greens and reds fading into the gentle, soft darkness that is waiting for you. The great dinosaurs are settling into their long night, their colossal forms still and quiet under the pale starlight of a world that is now theirs to command. And just as their world has found its peace after the long storm, so too can your own mind begin to settle. There are no more worlds to explore tonight, no more extinctions to witness, no more dynasties to watch rise and fall. There is only the gentle, easy rhythm of your own breathing, a soft and steady anchor in the quiet darkness of your room. Let the weight of these millions of years dissolve into a light and easy feeling, the feeling of letting go, of drifting. Let the last echoes of the long rain become a soothing, gentle whisper, a soft and distant sound that carries you now toward a deep and untroubled sleep. The story is over. It is time to rest.